All set? Okay. Good morning, everybody. My name is John Snow. I'm a senior virtualization engineer at Red Hat. And recently, I have been working an awful lot on our API documentation. So let's go ahead. Just in case anybody is not quite sure, I'm about to say these words an awful lot. So QAPI or QAPI is both our schema format, like in the tree, and our code generator for operating on those things and generating lots and lots and lots of stuff. QMP is our machine protocol. That's the actual API format that we have. So there is a small difference between QAPI and QMP, and if I use those terms interchangeably, forgive me, they're really close. QAPI doc, similarly, is the name of our source code format and the doc generator of the same name, and Sphinx is, of course, our documentation generation framework. So today, I would like to talk about the problems I have with our docs, what I am doing to fix those problems. I would like to cover some of the new syntax for how to best leverage this new documentation, and I want to talk about some of the problems and things we have yet to solve. If you zone out for the next 25 minutes, there's just a couple of things that I really want you to take away from this. The source format isn't changing a whole lot, but it is changing a little, and if you are maintaining lots of things, it may be useful to know exactly how I'm, moving your chair around on you. Some new features that I want doc writers to consider using. I want to explain how to debug when the new generator breaks to lessen people's frustration with the changeover. And at the end, there's some things that I kind of want people's input on because I've been alone in a room for 4 months trying to figure out what the best way to do this is. So we'll start with the problems that we're having. I just want to be clear that I'm about to mention a bunch of problems I have with the docs, but that's not meant to disparage people who have worked on the existing docs. They did the job that they had to at the time. I'm just obsessed and I wanted to do it better. So thank you for everybody who's worked on what we have. But if I make fun of Marcus, he'll forgive me. So for problems I have with our existing docs, number one, we don't have an index exactly. We have a table of contents, but it's organized by module and it's organized by however we have it laid out in source. So it's kind of difficult to get a list of commands. It's hard to know at a glance, hey, what are the commands that we have in this version? What are the events that we have? What do I, as an external developer, need to know about this version of QEMU? And it's kind of hard to figure that out at a glance. Yes, we have API commands to list these things, but, well, you'd have to know about that API command, so chicken and egg type of problem there. There's no cross-references in our existing doc, so everywhere we have littered, oh, see this command, see that command. Well, I'd love to. Would you help me find it in this giant, multi-megabyte HTML file? No. Use Control F, maybe. I don't know. Help yourself. So this has long been a frustration for me. So that's another thing I would like to fix pretty desperately. The documentation itself is incomplete. We often have commands or other structures that just say, yes, the members of this other thing are what comprise this. When we start layering things kind of deeply where we have shared structures between things, you're going to have to hop back and forth quite a lot to figure out, oh, well, what actually goes into this object I need to send on to the API. So that can be a little frustrating sometimes when you're trying to figure something out quickly or share information with someone else where you can't give them a single page to look at. They have to hop around. We have missing returns information for some of our commands. If we just didn't document it in the QAPI source, it doesn't show up in the HTML either. So this command returns something. What is it? I don't know. Good luck. The URLs that we have for the documentation are not stable. You can see there the little anchor tag is QAPI doc 390. That changes depending. It's just based on how many things you had in the docs that day when you built. So how long do you think the little URLs in the corner are actually going to be valid for this presentation? They might be wrong by the time you download the slides. I don't know. So it's hard to share information for our docs in a reliable way. This is subjective. I think the visual contrast is kind of poor. It's hard to tell where certain sections start and end because of, the members header maybe looks a little less interesting than the fields, which have that kind of horizontal rule background applied. And when you have hundreds of screenfuls of this, it's hard to kind of scroll through and at a glance kind of discern what you're looking at and why. This is a little more arcane, but our QAPI or QMP introspection, I should say, see, I said I would mix those two terms up. We don't reveal type names in our API. We reveal event names and command names, field names, but the names of the types of those fields we don't reveal. But our existing docs use our source factoring, so we reveal all kinds of type names and things that are actually not API. We don't promise that these won't change. So a problem with the existing docs is we might lean a little too heavily on pretending like these are real things. They're real to us, the developers, but to users, they're fake, unreliable, and we shouldn't believe them. So this is my overall argument for why docs needed a revamp, which is that it's hard to get a feel for things by looking at our docs. If you have already been developing for QEMU, I think it's easier to figure it out because you already know a lot of the pieces of the puzzle. But if you're a newcomer here, I think it's difficult between the lack of cross-references, incomplete references, everything's fragmented between multiple different sections. It's really hard to actually learn anything for the first time using this as your primary source. So I'll talk about some developer problems I have. Our existing doc generator builds docutils nodes directly from the source. It uses a mixture of Sphinx directives and manual docutils node construction to sort of build our docs, but it exposes a lot of like really subtle bugs where Sphinx was not prepared for us to do that, because Sphinx has its own ideas about how it will modify the docutils node graph, and that causes lots of havoc. And the Sphinx APIs themselves are all based around expanding restructured text directives. So we bypass that completely to the, our own detriment of being unable to use the large majority of the Sphinx internal APIs. So it's pretty hard to fix or extend anything that we already have, because we decided to, blaze our own trail a little bit, and that makes it pretty tough to add new features right now. The syntax right now is confusing because of our decision to build our own trees. It's not clear when you can use restructured text where in the QAPI source documentation. We say you can use most, and that's kind of true from experience, but it's not well documented. It's not actually well understood. Certain constructs currently break our doc generator in weird ways that take an extremely long time to diagnose. And the errors that you get are not great. So here I've introduced intentionally an error down on line 17, and helpfully our make system tells you that the error is on line 9. So if you have long series of docs and you don't know REST that well, these errors may help you to lose all of the rest of your hair. So for my biased opinions here, each irritant, I think, on its own introduces a friction to people who are less familiar with QEMU, and it contributes to a negative perception in general. So whatever preconceived notions people already had, this makes it worse. And it doesn't matter if it's actually true or not, but first impressions matter. So I wanted to make sure that our docs were in a more usable form for people new to QEMU who are maybe experimenting with using it for something new or interesting, but I didn't want to scare them away. So I want to talk about some of the fixes I've made. We have indexes now. We have an alphabetical index, and we have an index for each type of copy object. So now it is actually very easy to go and see a list of commands, a list of events, and so on. We have cross-references, so there's no more see also. You can just actually click and jump straight to the command or event that's being talked about in the docs. We have cross-references for the types of each field of a struct, a command, event, etc. Everything is automatically converted, so if you are curious about the format of a deeply nested structure, the breadcrumbs are there for you so that you can jump through and not waste your time searching around the page. The cross-references work across all of our docs, not just the QMP reference manual. It works anywhere within the tree, so if you have docs that extensively refer to QMP commands or events, you can add cross-references there. And if there is any chance of bit rot, the cross-reference is going to Yelp if it breaks in the future. So this is a good way to cross-link your long-form prose docs to the QMP manual and vice versa to make sure that things are well interlinked and not rotting. We have gotten rid of the members of phrase in the docs, and now they are directly inlined. So any shared structures, anything that's referenced is pulled directly into the documentation. So each object has its own full reference here. Unions are also supported here. So when you have tagged unions and branches, there are sections that actually drop down so that you can see specifically the fields for each branch to keep things all on one page for you, except for block dev add, which is still like 18 pages long, but there's limits to my power. Internal type names now, they're leaked a little less often because we're directly inlining these arguments. We're not saying, oh, it's the members of such and such, which is a fake type name. So there are actually a good number of types that have been removed from the docs because they're no longer necessary. They've been directly pulled in. So it's not perfect. I'm still leaking internal type detail to some extent. For instance, like sync, mirror sync mode, like the name of that type may not be API, but it's an improvement. I'm not perfect. Returns information is now definitely always included. Even if you don't write a description, we're still going to generate that type info for you so that it's there and fully documented in the output. The URLs are now quite a bit more stable. There's no more auto-generated IDs. We have the name of the object or the definition straight as the anchor now. So links that you give to other people, blogs that you write off-site should be an awful lot more stable now, and you can rely on them working into the future. Marcus points out that I put the name of the module in the tag name, which is not stable, but I'll probably be getting rid of that by the time we merge. So just didn't have enough time to make the change before the talk. Biased opinion again, but I think the visual contrast between sections is now a bit better, so it's faster to scroll through at a glance and kind of get a sense for exactly what you're looking at. Things are indented a bit. There's a slightly different color in the banner so that you can see section by section what you're looking at. Words have been wrapped to a much smaller visual column so that it's easier and nicer to read, things of that nature. So I think now, with some of the changes I've made, it just makes it a slightly better reference that you could possibly learn from. I think it is easier to get like a feel for a command with just like a single screen full of information. And importantly, the docs are now leaning towards QMP and away from QAPI in terms of the factoring and the way in which we're presenting information. Instead of relaying the developer factoring as is, we're trying to show how QMP actually is, the protocol people are actually using to talk to QEMU. There's a new architecture now for the doc generator. We're generating an intermediate REST and not docutils nodes directly, which allows us a much better reuse of the Sphinx APIs. it was based on Sphinx's own Python domain. So I thought, hey, if it's working for them, it probably is going to work for us. And there's a lot fewer bugs in our doc building because of that. As a result as well, you can now use any REST markup, except section headers, which I guess I could enable if you really wanted, but I think it's fine without. But pretty much any REST you want now does work. But if you hate REST syntax, I can't help. I'm very, very sorry. And best, the errors are now actually line accurate. So even though I've added a new intermediate generation step, you still get pointers to the original file and not the intermediate REST. And the line locations are improved as a result. So it's just better across the board. And how much time do I got? 5 minutes? Less than 5? 7 minutes, incredible. So this is all enabled by a new Quapi domain plugin. It works like Sphinx's Autodoc if you've ever used Sphinx Autodoc, which automatically generates a bunch of Python domain directives to document source code. I've modeled our Quapi domain directly off of that. So instead of Autodoc, we have QuapiDoc. And instead of the Python domain, we have the Quapi domain. So we have in our REST source document, we have the QuapiDoc directive, which invokes the QuapiDoc generator, which invokes the Quapi parser, which builds the schema. And ultimately, it generates this intermediate REST markup that contains all these new Quapi domain directives. And then Sphinx performs the final parse using the Quapi domain plugin to parse those directives. I was going to cover the Quapi domain syntax, but there's no time. So it is in the slides on pre-talks if you want to see exactly the new intermediate format, but I'm skipping it. I want to point out that when this goes live, if you're having problems, debug equals 1 is going to write that intermediate REST straight to disk. So this is what you would get. You get a nice 2-column output showing all of the source lines and the generated REST in the other columns. So if you're having weird REST errors that you can't quite figure out because the context doesn't make sense, all you have to do is use debug equals 1, and you can look exactly at what it generates, which has helped me immensely in the development of this. So I'm hoping it is useful for you. We have new cross-references, so there's ways to get at specific things using this kind of elaborate syntax. But over here, there's shorthands. You can use the last form, the any reference will generate a cross-reference to any Quapi entity now. I have changed the note section to the note directive. So that's one thing I've gotten rid of in our source tree. There's no more note section. We have just the directive for it, and it generates like that. Examples is now QMP example. This one's a little more custom. This one supports mixing prose and code together so that you can give longer, better examples. And that just looks like this. It just applies some QMP lexing and validation, gives you a nice little title box. It's a little better than our old example section. The other big change is that in the Quapi source, text is split into kind of an intro and a detail section now. Before, it was just untagged sections in general, and we called the first one of those the body. Now we have an intro and a detail section where the intro is not pulled into other entries, but details are. Because the intro is often things like, oh, this is a type that helps you achieve happiness, and that doesn't need to be pulled into every other definition that uses it. Whereas details often has things like examples, notes, warnings, things that you probably do want to see in anything using it. So that kind of looks like this. There's no real source change here, but there is a semantic change where you have to consider the difference between things you want dropped if this is a structure that's inlined, versus things that you want to include. So there's like a small mental change here. But there is a problem where, yeah, if you don't have anything that separates them, the parser can't figure out exactly what you meant if it doesn't know. So I'm still working on this. We might add a details tag or some other trickery to figure it out. For now, we're using to do as a gross hack, but we're working on it. And I will go super quick here because we're running out of time. Yeah. We still have synth sections in the code. We want to get rid of them. I worked on a parser that parsed all of the historical QWAPI schema that we have to try to auto-generate this, but it's complicated, so that's in progress. That's not going to be for V1 of this patch set. A problem with the synth tags as well is the difference between QWAPI and QMP. Sometimes we've written these synth tags to mean, oh, this is new for this structure since version such and such, or oh, this is new in the resultant user view in QMP since version such and such. So as we're recombining and shifting context of how docs are displayed, we need to check that this synth information is actually correct. I think it is in most cases, but I do need to audit it. I don't know for sure. And then there's some brief issues where I've tried my best to see like what would look best, but I do want people's feedback on like visual aesthetics and layouts and things. So if you want to check out the docs on your laptop later and kind of look over some of the decisions I've made and see if you just have any, I'm inviting bike shedding very intentionally. I would like to see it because I want people to be happy with this. Things like ifconnd, I wasn't quite sure what to do with, if we want those to link anywhere or do anything special. I've kind of stuck them in 2 places at once because I was that non-committal. So if you have strong feelings about how this information should be displayed, please let me know. Sphinx version compatibility as well is a bit of a problem still. We're requiring 343 at a minimum. I have it working. The code to do it is very gross still. So, if there's a way to avoid going all the way back, I would love to hear about that. Okay. And then there's a couple of other smaller issues that I'm still looking at and don't have time to go into the detail. So I'm going to skip to here. So the source format didn't change a lot, but there's a few details that have changed. I want developers to start looking at using the cross-references both in and outside of the QWAPI portion of the docs. I want people to remember that debug equals 1 will generate the intermediate rested disk. And I'm hoping to get your feedback on some of the slides I had to kind of cram through at the end. So there we have it. Nobody wants to yell at me? Why not? Yeah.
I just want to say something you didn't, namely what a massive improvement this is, number 1. And number 2, how I couldn't have done this. Because if you touch anything, you get like 5 screenfuls of backtrace from things. And I go, okay, no, not going to do that. You're different.
Yep. I'm filled with bad ideas all of the time. So just in case, if anybody wants the slides or wants to see the HTML or any of the tools I've developed for this, they are linked on pre-talks, and we're good.
Yeah, the KVM forum, the keynote a bit stretched, so we will stretch it over the coffee break just a bit. I don't want to steal a presenter's time, so I will steal yours. So sorry.
So, how to set up?
Yep. Yeah, HDMI. It's okay. Yeah, Mike. If you are thirsty, you can drink water. We will be showing you time. 25-minute talk, 5-minute Q&A. Is it okay?
Sure.
Yeah. I will be showing time. It's for the after that is the Q&A.
So we're from Intel and mostly working on the hardware feature enabling in the virtualization, KVM, QMU, and other VMM. So yeah, today we want to share our work on the to optimize the VM performance on the Intel Hyper CPU platform. So it's a client CPU. So yeah, I think people might be curious why virtualization on client is making sense. So I think in recent years we have seen a lot of cases and also other customers want to like to use the client system to run the VM workload. So that's why we are trying to see how we can optimize this on the because Intel from I think 2 years ago from Alder Lake, all the client CPU is hybrid. So yeah, let's get started.
Okay, thank you. Our talk will cover these three parts. First, let's have a look at Intel's hybrid platforms and have a look at its hybrid topology. And then we will introduce our hybrid CPU topology proposal in QML. And then Zhenyu and I will introduce our scheduling solutions in guest for Windows guest and for Linux guest. Okay, Intel introduced the hybrid CPU architecture from the Alder Lake. And this is an example of Media Lake. We can see that there are two dies, the compute die and the SoC die. The die is hybrid. And in the compute die, the module is also hybrid because there are two types of modules. One module contains the core. The core named, it means P core. And another module. Okay. Another module type contains 4 atoms. Atom is E-core. So the module is hybrid. And the core is hybrid too. Yeah, there's a core, P-core, and the atom, E-core. And there's atoms in SoC die. This is a low power E-core. Although the atoms in SoC die and in the compute die, they have the same macro architecture, but they have different frequencies. And the thread level, thread is also hybrid because the P-core has 2 threads and the E-core has only single thread. And for the cache topology is hybrid too. The P-core's module, in the P-core's module, there's one L2 cache. This means one P-core will has its own L2. But for the E-core, the 4E cores shares one L2 in the SoC die, in the compute die, and on the SoC die, 2 atoms shares one L2. And L3 is also hybrid because the compute die has a L3, but SoC die doesn't. The L3 is the only way to identify the atoms, whether on the SoC die or on the compute die. So there's maybe a question, why does guest need to care about hybrid CPU? Yeah, we test the single core performance in the guest by running the vCPU thread on the different cores. We can see that there are 4 atoms, single core atoms, and on each 4 atoms, the P core could have the better performance, but the low power core has the worst performance. So the performance is the most important reason for us to enable the hybrid CPU for guest. And another reason, because some guest OS has a special optimizations for hybrid CPU. For example, Windows 11, it has optimized its scheduler based on Intel Thread Director feature. And another reason is the feature. For example, the hybrid PMU. The PMU on the hybrid client platform, yeah, different cores have the different PMU events. And currently, our hybrid CPU solutions are mainly used for the gaming case because the game requires better performance, but the client is a resource-limited platform, so any improvement is very important. And there's another hot topic about vCPU pin. We believe that pin vCPU is a precondition of hybrid CPUs in guest. If we don't pin the vCPU on hybrid client, then the vCPU may migrate to different cores. Then the hybrid information in guest and in host will not match. This will hurt the performance. And there's the double scheduling issue. Double scheduling is not a client-specific issue. The cloud keys also has this issue, but since the client is resource limited, this will hurt the performance significantly. This means there's 2 schedulers. One is in guest and one is in host. If we don't pin the vCPUs on host, then both 2 schedulers could work, and the concurrent scheduling results in more task migrations and a context switch. So the hybrid CPU information is important. How to configure it to the guest? We have the proposal. Currently, the QMU configures the topology by SMP command. With the SMP, then QMU creates a CPU or cores object. For x86, there's a special array named possible CPUs. Each element in possible CPUs is mapped to a CPU object. And for the PPC, the element of possible CPUs is mapped to the core object, and the CPU object is created in place under the parent core. But this is not enough. We can rethink the mid-lake example. All the CPU topology level may be hybrid. The hybrid die, hybrid module, hybrid core, hybrid thread. So if user want to configure the hybrid topology, then we need more topology devices. So this is our first step to the hybrid topology. We need to abstract each CPU topology level as a device. Current, we already has these three devices: CPU device, core device, and the cluster device. But to complete the topology tree, we need more. For x86, we need the socket device, die device, module, core, and thread. Then how to connect the different device? In our RFC, we introduced a virtual CPU bus. Currently, the bus structure in QML could manage the topology very well. It is used in the CXL and PCI to manage the device topology. So I think it's very natural to also use bus to manage the topology relationship. Then with the such device, we could allow the user to build the device tree through the command line. This is our hybrid CPU topology proposal. Yeah, allow the user to custom their own device tree. For example, this socket 0 could be created by the device command. Yeah, device command creates a CPU socket and the ID is socket 0. And then the die 0 and the module 0, module 1, and the P core and the E core. And at last, the user could connect the threads to the P core and E core. And there's additional benefits. With so many topology devices, then we could reflect the topology relationship in the QOM path. Now, we could reparent the child device to the proper parent device, and we eventually will have the QOM path to reflect the topology relationship. And maybe we could support other level hot plug, for example, the socket level hot plug, because now we have the socket device. And for x86, it could help to emulate the features which has a topology dependency. Currently, QML supports running average power limit, this ripple feature. This feature has registers, which is a package or die scoop. When we have the socket and the die device, then we can save and load the registers in such device, and all the topology child could share the same register value. There's our idea. We also want to go further to support the hybrid cache topology. This means we also want to abstract cache to device 2. For example, there's a L3 cache, we could create by the command line and specify its parent as a die 0. So all the child device under the die 0 will share the same as L3. We have posted our V2 RFC to the mail list. Yeah, it's a very huge work. Welcome your feedback and comments. And then Zhenyu and I will introduce our scheduling solutions for the hybrid guest.
Yeah, so besides the hybrid topology issue that we have to resolve, right, how to define that for the guest, and then we actually have other scheduling optimization. So because hardware not just provide hybrid topology info, but it has other features that can provide some performance and energy capability of the CPU at runtime and to help the OS scheduler. So this is Intel calls this the first version is the hardware feedback interface, and the second version is the Intel thread director. It basically provides a table in the memory that can you can see that each logical processor will have a line of definition of the performance and the energy efficiency. So in initial version, it only support one class. So you can check the change on the hardware, and the second version ITD has added the classification support, which means that it can track the instructions that the application running on the CPU, and it analyzes what's the class based on the instruction, IPC based, and it will provide you a class. So this class you can reference this as the indicator from the hardware that which is the best column you can search to what's the indicator you want to use. So if you want to use if OS scheduler want to more performance schedule, so it will check the performance columns and it can compare the ratio right between different processors. Or if you want to currently want to more energy, and you can compare the energy column. So that's the basic idea. And hardware will also can be notified the OS scheduler through the thermal interrupt. So any change in the in this table from the hardware will be notified to the OS scheduler. So yeah, we know that this feature, hardware feature, has been enabled in the Windows guest. So we want to see what's the benefit, right? What does it really help? So we do this a lot of combination testing, right? The baseline is the without hybrid topology, but only have SMP topology, and we also add several options like enabled ITD virtualization or setting the CPU affinity. So from our conclusion, this is a 3D mark in Windows 11, and we can see that all those things combined has reached the best result for us. So with the hybrid, so the result is that we need to combine these three elements to get the best result. So this page is how we currently do the ITD virtualization. So I think it's very straightforward. So we try to emulate several ITD related MSRs. So how to set up the table for the guest, and we have KVM is talking with the Linux host HFI and the ITD driver, which basically set up the table in the kernel, and KVM can get the information from the driver and provide a virtual table for the guest configuration. So yeah, that's basically the idea. Yeah, but we know that even with this might not be enough for the Windows, right? So we have several dependency. One is I mentioned that we need interrupt support, which is thermal interrupters. We have to add the thermal interrupt injection in the KVM. And also we have other maybe unknown unsure dependency, but we add that anyway, like the ACP, ICP, PC table. So Windows guys just told us it might be required, so we just added that. And also we future, so we like to move this dependency in the user space based on the recent QML user space MSR handling framework. So yeah. This is our, we actually send the patches to upstream, so I've got some comments. Yeah. Okay.
Okay, the last part is about the Linux guest, how to optimize the scheduling in Linux guest. Linux guest use ITMT scheduling. ITMT is Intel Turbo Boost Max technology. This means some CPU cores can reach higher turbo boost frequencies, and thus these cores have better performance. And ITMT scheduling detects cores with the highest available turbo frequencies and prefers those cores to place tasks. On the hybrid platform, ITMT scheduling implements priority order as the first P call, then E call, then low power E call. Low power E call means the item on the SOC die. And at last, it can consider the PCOS SMT thread. There are two keys. For new created task, scheduler will first consider to place it as the free PCOL, then free eCall, then free low power eCall, and at last, scheduler could place a task to the PCOS SMT. And there's a same logic at the idle load balance case. The scheduler could consider to pull the extra task from the basic call to the free call. It first considers the P call, then free call, then free low power call, at last the P calls SMT thread. So for the SMT scheduling, there are four cases based on two conditions. That's whether to enable ITMT in guest, whether to ping vCPUs at host. Of course, there's the worst case. This is the right case. This means we enable ITMT in guest, but we didn't ping the vCPU on host. Then the guest and host both have the hybrid knowledge, but since we didn't ping the vCPU, then the vCPU thread could migrate to different calls, and the guest will have the wrong information. This will hurt the performance. So we can compare the other three cases. The first, this is the case that we ping the vCPU at host, but we compare the guest with or without ITMT. Look at the left picture. We run the single call benchmark in guest for 10 times. And for the guest with ITMT scheduling, the result is very stable. And compared with the right picture, we can know that all the single thread running at the P call. But for the guest without ITMT scheduling, the result is random, and the task may run at the low power call or eCall or P call, so the performance is unstable. So now we have the conclusion. If we ping the vCPU at the host, then it's better to enable the ITMT tool in the guest to have the best single call performance. And then we can compare that case that for the guest, the first case, we ping the vCPU at host and enable the ITMT in the guest. Then, since the vCPU is pinged, the host's scheduler won't work, but the guest has the ITMT scheduling. Its scheduler has hybrid knowledge. And another case, we didn't ping the vCPUs at host, and we also didn't enable the ITMT in guest. Then, since the ITMT scheduling is enabled on host by default, so the host scheduler has a responsibility to optimize the hybrid scheduling by schedule the vCPU thread. We use a Hackbench to compare these two cases. We can see on Hackbench, the guest with ITMT, also with ping vCPU, it can achieve the 8% improvement. This is mainly because the vCPU is pinged. Since a vCPU ping could reduce double scheduling overhead, it can significantly reduce context switch and CPU migration on host. So we have the conclusion for the Linux guest. The best option to get the best performance, we need to ping the vCPU first and enable the ITMT scheduling in guest. Currently, this work is under the POC state. We implement the virtual MSRs to give guest a highest performance hint. And then guest can cite the ITMT CPU priority based on the hint. But we also want to use the PVSCAD framework, which is proposed by Google in KVM mail list. This framework is a more general way to improve guest and host scheduling, and we can apply ITMT to this framework. And at last, I also want to thank my other colleagues. They helped us to bring this topic to here. Yeah, thank you. Do you have any questions?
Okay. Yeah. What do you think are the main uses for virtualization on client platforms? Because that may choose whether you pin or whether you don't pin.
Yeah. So our current customer usage is we mentioned like the gaming. So they basically want to use the consumer setup and to run the remote gaming for the client.
So, sorry, what I meant is like gaming in the sense that you run full Windows VM all the time, or gaming in the sense that you start the VM just to play the game.
Windows VM.
Yes, but do you use then Windows almost all the time, or only to play the game and then you turn it off? Because I guess games you can only just pin them to P-cores and ignore that E-cores and low power E-cores exist completely.
Okay, yeah. So actually on system you have a multiple CPUs, you can have a different setup, right? So you don't have to use all the CPUs, but you can use part of that. That's okay. Depends on their VM configuration. So maybe they can run 2 or more. So yeah, that's okay.
And is there also use for developers? Like maybe developers may be okay with the E-cores, but gaming, yeah.
Right. So we have other cases like education. So they want to provide the education setup based on the VM, so that would be easier to manage and deploy to the students. So yeah.
So for education, you would also use the E-course.
Yeah, use the E-course as well.
Thank you.
So I think when we post these patches to the upstream, and we got comments to work on the hybrid topology first. So if you have any more comments about QML topology, welcome to discuss with us. So yeah, thank you.
Thank you all.
Okay, I heard that we're good to go. So good morning, everyone. My name is Kevin Wolf, and I assume you're here because you want to hear something about out of process storage backends. And I hope I can tell you something useful about that. So first, let me give you some background. I was already talking about out of process backends 2 years ago, and I was more going into the motivations of why you would even want to do something like that. So I'll just do a short recap of that, and then I'll go more into the details of the options that we actually have. So one reason why you would want to move the storage backends out of QEMU into a separate process might be that it just gives you better isolation, more security. You also have separation of concerns, like running VM is a different task than accessing storage, really. You might want to do log jobs, like merging snapshots, even while the VM is down. You might want to share a backing chain between multiple VMs and still delete snapshots in the shared part, for example. That's something that you can do when you have a single shared out-of-process storage backend. You might want to share CPU for polling, so for performance, it can be beneficial in some cases. Or you can share a single physical disk between multiple VMs using user-space block drivers like the NVMe driver that we have in QEMU currently. So all of these are motivations why you would want to use an out-of-process backend. Of course, I'm here because I have a specific motivation to do this. Yours might be different. The talk still applies if you have a different motivation. I'll explain the characteristics of the different methods we have to achieve this. Your conclusion might be different than mine. So my specific motivation is that in the context of KubeVirt, storage is kind of considered someone else's problem. Storage is just something that's provided by Kubernetes, and then you run a VM on it. And the basic idea for that is the storage vendor just provides some software, a CSI plugin, that provides all of these operations on the storage. And in practice, we see that either the CSI driver doesn't even exist for your storage, or it does, and it doesn't quite meet the requirements. For example, it's often the case that when you request a new volume on the storage, it gives you a whole new LAN, and that just doesn't scale well if you have thousands of LANs in a Linux kernel. So from the past, we know QEMU can already do all of this. So what we want is to expose that and be able to use it in the context of Kubernetes. So that's the context in which my team is looking at this. So what are our options to achieve this? The obvious one that everyone knows is NBD. We have been using this for a long time. It's been the first export in QEMU. We're using this mainly for migration. And that's exactly where its strength is, because it's a network protocol. You can use it over the network. But you can obviously also use it locally. So you can export NBD using a Unix domain socket and then just connect the QEMU process to it. Its advantage is also it has existed for a long time, so we know it works. And if you want to, you can even attach it as a host block device. As you can see here on the diagram, it's a relatively long I/O path, like both QEMU and QSD are involved in that. I'm using QSD for the external out-of-process backend. Could be any storage daemon, really. So you could plug in something else. I'm also showing both ways, either QEMU exporting the Unix device, domain socket, and you're connecting QSD directly to it, or you're going through an NBD block device on the host. And one of the problems with MBD is, as you can see, performance is not quite the same as if you do it in process in QEMU. Which is, as I said, it's a long I/O path, and also you do a lot of copies. The data that you're writing or reading is copied into the socket, is copied to the QSD process. So it's not really the solution that we want, and you probably already guessed so. Another problem in our context specifically is that if you have a socket is not a file, it's not a block device, but Kubernetes really expects storage providers to provide file systems or block devices. So it doesn't really match that. Except if you attach it to the host as a block device, you can do that. The problem is, I wanted to show you the numbers for this, but the benchmark didn't even complete. Like, the connection aborted. The kernel block driver was never really happy with the MBD connection. So, well, maybe not what you want to use either. Then we have a fuse export type, and we haven't talked about that much. I believe it doesn't get a lot of attention. It reduces the copying that you have. It's still not zero copy. So it does support splicing, so it could be achieved in theory. We don't do that. You still have both QEMU and QSD in the I/O path. But the nice thing is the export shows up as a regular file, so you don't have the problem with having a socket. And it works as a regular user. So while even attaching MBD to a block device requires root permissions, this just works. How does it perform? I compared actually two different Fuse implementations. Fuse master is what we currently have in QEMU. It's not great. Hana wrote some patches to improve the performance there. And it's a bit better than NBD anyway. And then we have the option of vhost user block, which I believe is what most expect, that it's the solution to do this, to have out-of-process storage backends. And it's radically different from the other two solutions in that it completely cuts out QEMU from the I/O path. So what you do is you share memory between a guest, like the guest RAM, and give QSD, the external storage daemon, direct access to that. It also doesn't require privileges. You just have shared memory. You need a Unix domain socket again to communicate between QEMU and QSD to set everything up and to share the memory. So this one should perform the same as in process. In theory, in practice, it seems it's sometimes even a bit better. I don't know exactly why that is. But also, it doesn't share the same virtual block implementation, like the processing of the virt-q. So it's possible there's some difference there. Of course, that comes with different problems. So as I already said, it requires a socket. We don't have a block device or a regular file in this case. And it requires the guest RAM to be shared memory, so that this actually works, that we can get this short I/O path. And there have been discussions before if we should just enable shared memory for VMs by default. And the answer was always, no, we don't really want this because it conflicts with other features, such as kernel same-page merging, memory ballooning, and a few others. So it's not something that we really want to do if we can avoid it. It also only works optimally if you use a virt-io block device, because what vhost user block is essentially using the virt-io block protocol to communicate with the external daemon. You can work around it by using libblock.io. We have a libblock.io based block driver in QEMU that can access a vhost user block device and then can be used as a backend for anything else, like an IDE device, or if you want floppies or SCSI or whatever. But obviously that means that you have to go through QEMU again. You lose the advantage that you have the shared memory with QSD. Also, this is quite different compared to normal block backends, because you don't really have a block backend on the QEMU level anymore. It's just some vhost PCI device that directly goes to the storage daemon and bypasses the whole storage, the whole block layer in QEMU. So for existing management tools, this is different, needs to be supported separately. And finally, we have a fourth export type, which is similar to both vhost user block and the other two, in a way. It's a single export type that exports to the VDPA bus in the host kernel. And then depending on how you use it, you get something that matches more or less vhost user block. That's the diagram on the left. Or you get something that matches more the NBD or Fuse use case. That's if you use the VDPA driver that essentially exposes the exported device as a block device on the host. And what you would expect is that they behave similar to those as well. So the nice thing about this is if you have both use cases on the same machine, or on the same daemon too, you only need to support a single export type. It's both VDUs, like the QEMU storage daemon side is exactly the same for both sides. And then you can decide when you use the exported block device if you want to use it with shared memory or if you want to attach it as a block device and use it that way. With VDPA, you need privileges for both modes. So while vhost user block and Fuse work without privileges, VDPA, you need privileges to attach the export to the VDPA bus in the host kernel. And obviously, that also means that you need kernel support. And it's not necessarily there in all distros yet. So you still have to select, do I want to use the shared memory thing? And then you have to use, in this case, not a socket, but a character device, which is still not a block device or a file system that we want to expose to KubeVirt, in our case. Or do you want to have a block device, but then you get the slower path? So one crazy idea, I'm not sure if that's realistic at all. What if the block device had an IO control convert me into a vhost thing? It would make the block device inactive, would only return EBC or whatever when you still want to access it. And then the VDPA device actually transferred to the vhost kernel driver, and you get back a vhost character device. If we did that, then we could just pass a block device to QEMU, and it could transparently try, can I convert this into vhost and use the more optimal storage path? Like, as I said, it's a somewhat crazy idea, maybe some food for thought. I don't know. So how does VDPA perform? This looks pretty nice when you use the vhost path with shared memory, even a bit better than vhost user. That's actually something that I haven't found an explanation for. Like when I said before that vhost user block is a bit better than in process, I can explain that by it's two different implementations of the virt queues. That's not the case here because vhost user and VDPA, they share the same code. So there's some difference somewhere else. I actually found one difference, and when I tried it out to change it in vhost user, it didn't change the result. So we could maybe look into that, where the difference really is. What's next? Oh yeah, I talked about how you can use libblock.io if you want to have the shared memory path, but still not use Virdeo block as your guest device, right? And if you use libblock.io, you get a normal QEMU block backend, as if you were using just a local image file or block device. And you can use that with any kind of guest device that you want. And the performance is not worse than if you attach it as a block device first. So if you're okay with the requirement of having a character device instead of a file or a block device, and you're okay with using shared memory, then you probably want to go the vhost VDPA path. And for anything that is not Virdeo block, you can just use libblock.io, and it will perform fine. And finally, we have another possible block backend that doesn't exist in QEMU yet, and that is uBlock. We had some talk about it. The IO path actually looks quite similar to Virdeo VDPA. You have you go through QEMU. QEMU accesses a block device, so it's actually a block device. So that's nice. That's what we want to have. And then you have the QEMU storage daemon, which accesses the corresponding character device, sends requests there, basically commands fetch a request, and then uBlock just forwards the request, and QSD can process it. We don't have an implementation in QEMU for that yet, though it's doable. While trying to implement something, I didn't do it in QEMU for now, but I started with the Rust storage daemon. I noticed that the kernel driver is not very mature yet, so there's some work left to do there. But it's, you know, if the theory is what we want, then we can work on that and improve it. So how does this perform? This is a bit harder to tell because, as I said, it doesn't exist in QEMU yet. So what I had to do is use the UBD server, which belongs to the uBlock project. And it does things a bit differently because all of the things that I benchmarked so far in QEMU, they use the single thread. Now, UBD serve uses one thread per queue, and I tested with 4 CPUs, so get 4 queues and 4 threads. So these are not completely comparable. To make it comparable to in-process at least, I ran the in-process benchmark once again with 4 IO threads assigned to the single device using the multi-queue code that we merged only recently. And that's what you see on the left now. So performance is not bad, but it's also not in the level that you get with shared memory like in vhost user or vhost VDPA. So what's the conclusion from all of this? I really want to take some properties from each of the things. Like everything that we want exists somewhere, just the combination of everything doesn't really exist. In particular for performance, it seems important that you have 0 copy and also that you don't have too many context switches like the shorter IO path it shows too. But the problem is that sharing memory and giving access to the memory from the storage daemon is kind of painful and it costs features. Yeah, you can't use other features. Anyway, if the privileges are not a problem, and if you don't have a problem with shared memory, then VDPA seems to be a good export type that performs well in both ways, like vhost VDPA and the Virdeo one that exposes a block device. But obviously, you still need to do that trade-off when you choose how to attach it to the host. Now, obviously, the question is, can we improve anything here in the situation? And if yes, which export type do we want to improve. So for us, it seems that we almost certainly want a normal block device or file, which already limits us to the export types that currently don't perform as well as we would like them to. But the limitations of shared memory just seem hard to overcome. I don't see how we can improve there, though it was mentioned to me that some people are working on it. Maybe we will get an option there. And bypassing QEMU's block layer also makes the management very different, so it's more difficult for management software to work with this. So we really want to have a block device or a file. And in that case, we don't really have a way to remove QEMU from the I/O path, except I had the thought, there was talk a while ago about doing an I/O urine pass-through, and in that way, the guest could directly access the block device. I'm not sure if that's something that's still under consideration or not. That would maybe be the only way out there. But what you can do is try to reduce the overhead on the QSD side. Like so far, we have always tried to remove QEMU from the path. Maybe we can do something on the side of the external daemon. So one optimization for uBlock that is currently on the mailing lists is something that actually provides zero copy. Because often the user space daemon doesn't actually do anything with the payload that you're copying into its memory. The only thing it does is it takes it as a buffer to write to an image file or to read from an image file. So there's no real reason to even copy it into user space. If you could just access it with the next command that the storage daemon is issuing to the backing image. And if it's using I/O urine, then with uBlock that can be done in that way that you couple two requests. The first request to I/O urine is give me the buffer that is related to this request I just got from you, and then do a read or do a write using that buffer, and it never goes to user space. So this one is in review upstream. I expect that sooner or later this will probably be merged. The next thing that we could do, and that I wrote a prototype a while ago for, is what if you skip user space completely? Like in many cases, the user space doesn't do very complicated things. It just maps things to a different file descriptor and a different offset. And we can just cache that in the kernel and then not call into user space at all. So in this case, we're not cutting out QEMU from the I/O path, but we could cut out QSD from at least the hot path. And only if you need to do, I don't know, allocate new blocks or something like that, you still go to user space. And then another idea that came from that, from Ming-Lei, is, well, if we're moving things into the kernel, why not have code in the kernel? Like you upload ePPF code to the kernel for handling requests. Then you can only do mappings, but you could also do things like updating a dirty bitmap, stuff like the QEMU block layer usually does. You could just do that in the kernel as well. There is some early prototype code for that. I don't know what comes out of that, or if it's a good idea even. And finally, I have made a few other optimizations, observations, what you could optimize in other block drivers. So the first thing is the difference that I noticed between vhost user block and VDPO block. They have different queue size by default. That seems to be an accident because it was updated at one point for all of the VDPO block implementations except vhost user. So we probably should just fix that. But as I also said, it didn't really fix the performance difference. I also mentioned that uBlock, the default server, uses multiple I/O threads. We should probably implement that for exports as well. Like we did for the VDPO block device itself, export should do the same. And finally, something seems to be wrong with the MBD implementation. It performs slower than I would expect from the thing that it's doing, like from the architecture. So finally, I only have some bonus data. That's mostly for when you view the slides after the talk. These are all of the results together. First, for a null device, which shows purely the overhead of the transport. So I think that's maybe one of the more interesting ones. And as you go to slower storage, to disks, you see that most exports perform roughly the same because the disk just slows things down. And finally, I did the same on an encrypted file system, my home directory on a laptop. And you see, MBD is the one that really doesn't perform well there. There's something else going on, like it's not handling parallel requests right or something like that. And that's all I have. So if there are any questions.
I hope I remember everything that I have to ask. Can you go to slide, I think, 23?
23?
Yes.
This one?
Yes. When you say bypassing QEMU's block layer, do you mean QEMU, or does QSD also count as QEMU block layer?
No, in this thing, I mean bypassing QEMU's block.
Okay, so it's like it also makes it different if you can write QMP commands to storage daemon, it's still pretty different.
Well, I mean, even the fact that you need to send things to the storage daemon is quite different from what you used to do. So
yeah. So second question is when you use libblock.io to convert the host to a random device, can it do like stuff like map the guest memory and pass the mappings to the host user so that you can do the DMA into?
Yes. So it still uses shared memory.
Yeah. Yeah. Exactly. Yeah.
I think that how efficient that is, it depends on whether the guest device actually supports that. Like, I believe vhost block has some specific code to enable that, right, Stefan?
So I think the idea is roughly similar to the NVMe backend, like where in that case you have to pass it to VFIO. In this case, you pass it to the host user, the memory map of the guest. Yeah,
so basically I think you have to register the RAM with the backend, and when that is done, it just uses the shared memory.
And third, and sorry everybody, but final question. For the privilege issue, have you looked into using Satan?
No, I haven't.
Okay.
Maybe I should.
Thanks. So one comment is you said, I'm not sure why VDPA was so fast in some cases.
Compared to VS user, yeah.
I don't know if it's still the case, but VDPA pinned memory in the past.
Okay.
So I wonder if all the guest RAM was all pinned, and maybe that affected the performance.
Interesting thought.
Yeah, should be the case. The only way when we don't pin the RAM is when we use you need a special flag to and so every time the address is mapped and unmapped. But yeah, the default case, it will pin the entire RAM.
Maybe we can test that.
Yeah. And I mean, just a question. Similar to, you mentioned that uBlock, with uBlock we can change it and make essentially make the uBlock device access directly the storage in one slide. Maybe we can do something similar also with VDPA, implementing the VDPA device into the kernel.
Yes, I think then you're essentially back to vhost block, like the in-kernel thing.
Right. And then you don't have the copy anymore in using Virta.io VDPA.
Right. I mean, it's a bit more challenging, I guess, than uBlock, because uBlock automatically sees this thing as a storage device, and in this case, you have to implement a Virta.io block, implementation in kernel. And it seems we're out of time.
Oh, so then okay.
So just catch me outside later.
I'm going to talk about IO-thread vert-queue mapping. IO-thread vert-queue mapping is a Vert.io block feature that was added in QEMU 9.0 that helps scalability of Vert.io block. So Vert.io block was optimized over the years, but typically with a workload that is running on one CPU, submitting I/O on one CPU, doing that as fast as possible. And the bare metal overhead, if you compare bare metal and you compare the virtual machine, that's what we've focused on. But on larger systems, larger VMs that have many vCPUs and a workload that's actually submitting I/O requests concurrently across all those across all those vCPUs, the overhead of virtualization is significantly higher than what you see with just one vCPU. So some of the numbers that I saw when we began this work was maybe 20% virtualization overhead, maybe even 30%, so way too high. And so that was something we wanted to optimize. And this is very important because nowadays virtual machines tend to have a lot of vCPUs, right? So this is not a high-end rare case. This is a common case nowadays. So we need to fix this. So let's start by looking at how the Vert.io block device is designed and how it handles scalability. Vert.io block is a multi-queue device. So it's possible to have many vert queues on your Vert.io block device, and then each vCPU can use its own dedicated vert queue. And the advantage of doing this is that the guest driver doesn't have any contention when it's submitting or completing I/O. It doesn't need to communicate or take locks in order to share just one vert queue. Instead, each vCPU has a dedicated vert queue that's operating independently and concurrently with everything else that's going on. The other advantage of multi-queue is that completion interrupts can be directed straight to the vCPU that submitted the I/O, which is where the application is running, where the caches are hot. So that's the best place to be. If you didn't have the ability to direct the completion interrupt to the right CPU, you would have to send it to an arbitrary CPU. And then that CPU would have to notify the actual CPU where the application is about this completion. And that adds latency. So this is very standard stuff for hardware design. Network cards have been doing it for a long time. NVMe, the NVMe PCI interface also is multi-queue in this way. And in fact, QEMU enables this by default. When you launch QEMU and you launch, say, a 16 vCPU VM, you don't even need to specify anything. Your Vert.io block devices will automatically have 16 vCPUs. So why does SMP performance still suffer, right? So QEMU implements this, it's all there. But why are we still slow when we have big VMs? So let's look into that. The answer is in how QEMU actually processes those vert queues. The Vert.io block design itself is good, but what's happening in QEMU when we process a vert queue is that in QEMU, a single thread handles all of the vert queues for a single Vert.io block device. So that's where you see this kind of funnel, this bottleneck shape, if you look at the diagram. So if we have 4 vCPUs in our guest, on the host side, we actually still just have one thread that is processing all of those vert queues. And it's kind of unfair because imagine you have 4 vCPUs that are all adding as many IOs as they can as quickly as possible. On the host side, you only have one CPU that's trying to process all of that for them. So how is it supposed to keep up? So that's kind of the hypothesis here. When I started this work, the idea is that this is a bottleneck. That's probably why we see these high overheads, 20% overhead or whatever the virtualization overhead is. And by the way, the work that the IO thread is doing in QEMU, it needs to parse the vert queue requests. And then those requests go through the QEMU block layer. There you might have the QCAT2 image format. You might have other block layer features. And eventually the block layer says, okay, here's a buffer. Here's a logical block address. Let's submit this IO. And it evokes a system call, maybe Linux AIO or IOU ring. And it sends that to the host kernel. And then the host kernel goes and it does basically the same thing again. It has to parse Linux AIO or parse the IOU ring request, sends it down the VFS and the Linux block layer. And then it sends that to the driver. So then the NVMe driver in Linux, for example, will submit that I/O, and then you take the reverse path up. QEMU will build the response, and it will inject an interrupt into the guest to complete the I/O. So that's a long path. There's a lot of CPU cycles doing stuff. And that also explains why this kind of bottleneck design becomes a problem, because as you overwhelm this one thread, it just can't keep up. So before we could actually solve this problem, I wanted to see what the performance improvement would be if we had this. And so what I did is I set up a simulation. I created a VM that had many Verteo block devices that were all actually accessing the same image file, the same disk. Normally you wouldn't do that because you would corrupt your disk, but I didn't have a file system on it. I was just benchmarking the block devices from inside the guest. And what that allowed me to do is I gave each Verteo block device its own dedicated I/O thread. So I was, in effect, simulating what if we had a dedicated I/O thread for every single queue, but I had lots of devices. And the result was that, indeed, you can get a lot more performance out. You can saturate your disk if you do that on a SMP guest, a guest with many vCPUs. Okay, so one thing I will point out is that on benchmark slides, when I have graphs, I have a GitLab link. You can go there. You can see my script, so you can get the command lines that I used. You can get the FIO benchmark results and an Ansible playbook to reproduce that. So if you want to dig into the details of the benchmarks, they're all there. Okay, so since simulating this showed that there's promise here, there's more performance we can get by doing this, we went ahead and did it. It's called IO thread virtue mapping. It was added in QEMU 9.0, so it's already there upstream, and you can use it. And effectively what it's doing is it's allowing you to take advantage of multi-queue on the host, not just in the guest. As you can see, it lets you assign vert queues to host IO threads, and that way you can actually get this concurrency. Implementing this took a long time. Not the Verteo part, but QEMU itself, in its history, it was single-threaded. So all the block layer code in QEMU has been single-threaded. And so Kevin Wolf and Emanuele Esposito and Paolo Bonzini and we worked on this for a number of years to make a truly multi-thread capable QEMU block layer. And Kevin and Emanuele presented the details of how they did that work in last year's KVM Forum. So if you want to understand what locking changes they made and what problems they found, please check out their talk. I'm not going to go into that this time. What I am going to do is I'm going to show you how to configure this for Verteo block devices. I'm going to talk about the performance improvements, show you my benchmarks. So yeah, that's what I will cover. So let's start with the libvirt syntax. So this is what you can use today. It's in libvirt 10. Peter Krempe implemented the syntax for us. And now you can add an IO threads tag to your disks. And you can give it a set of IO threads. You can tell it use IO thread 1, use IO thread 2. And those IO threads will be round robin allocated to the vert queues. So if your device has, say, 4 vert queues, because there are 4 vCPUs, and you want to give it 2 IO threads, it will round robin allocate them. So the first vert queue goes to IO thread 1, the second goes to IO thread 2, the third one goes back to IO thread 1, and so on. Because of the way that vert queues work, the vring shared memory data structure is a single consumer queue. So it's not the case that your vert queue can be serviced by any IO thread. Instead, you always just assign it to 1. That way we don't need to do any locking in the IO threads. Yeah, so that's how you configure it. I will show you the QEMU syntax as well. And in fact, we have some more advanced configuration you can do if you want. This is the QEMU syntax. In your device, you just add the IO thread mapping parameter, and you can give it an array of the IO threads you want to use. What I'm showing here additionally is that you can give it a vert queues array, and you can actually assign on a per vert queue basis. So if you want to go very fine-grained and assign individual vert queues to individual IO threads, you can do that too. You don't need to round robin allocate. You might be wondering, why do I want to do this? You probably don't. Most people don't need it. It's useful for devices where the vert queues are differentiated, where they're not all equal. And in Linux, the VirtIO block driver actually has a kernel parameter or module parameter where you can reserve queues and use them as polling queues. So those queues won't use interrupts, and they'll work slightly differently. So that's an example of where maybe you'd want to assign them to a different I/O thread. But in general, I don't think anyone needs this yet. I think that maybe for future devices like Virteo SCSI, it will be more important to have control over this because you don't just have one type of queue. Okay, so that was added in QEMU 9.0, along with everything else. Before I go on, I do want to point out there's confusing terminology. There are QEMU's I/O threads, and then in libvirt we also have I/O equals threads, and those are two completely separate concepts. I/O threads is what I've been talking about and what I mentioned. They're a feature in QEMU that allow the user to specify, okay, I want to have a thread, and then they can assign I/O device emulation to those threads. They give you control over which threads are doing the I/O emulation. I/O equals threads is a different feature. It's a user space thread pool. It's an asynchronous I/O engine that QEMU can use. You probably won't use it though because you'd probably rather use Linux AIO, which typically performs better, or IOU-ring on Linux. But on other operating systems, you might use I/O equals threads, and it's just a thread pool. It doesn't work very well with IO thread vert queue mapping, by the way, because you're still going to have an IO thread that does the IO emulation, and then it sends off the request to yet another thread, that the worker thread in the thread pool. So it's like, it doesn't fit very well, especially on Linux. I recommend using cache equals none and IO native. Okay, so I wish that was it. I wish it was very, very simple, very easy, nothing to do, and it could just automatically enable this feature and always use it when you need it and not use it when you don't need it. But there is some human configuration that's necessary. You need to choose the number of IO threads you want to configure. If you have too few IO threads, what happens? Well, then we end up with a situation like we had with one IO thread where we can't saturate the disk, right? So too few IO threads means your performance won't be as good as you can get. You won't be able to get all the IOPS that the disk can do. If you have too many IO threads configured, then you're kind of wasting those CPUs and they might interfere with your application. You really want to have a small set of IO threads and then use all your other CPUs for the application, which is the actual point of running your VM. So I did benchmarking and I found that usually 4 IO threads works well with local NVMe drives, and this will depend on the type of storage that you use, how fast the drives are, whether it's maybe network storage or whether it's local flash storage. But 4 to 8 is a good starting point, and if you need to get the absolute most out of it, then just run some experiments yourself and see what's best. Another thing is, how do you even assign these IO threads if you have multiple Virteo block devices? You can actually share the IO threads between multiple devices, so they don't need to be dedicated. And this is a very common use case. Often you might have a system disk or a boot disk with your operating system, and a separate data disk where the actual workload is going to be doing most of its accesses. And in that case, you don't need to have dedicated IO threads just for that boot disk. You can go ahead and share the IO threads. It won't really impact performance because it's a low utilization Virteo block device that won't interfere. So you have that flexibility. If you want to have multiple Virteo block devices sharing the same IO threads, you can do that. Okay, and when you have multiple threads, one more thing you can do that will help performance is you can pin them to host CPUs. If you do not pin them, then the Linux scheduler on the host will just run them where it thinks it's convenient to run them. When you pin them, on the other hand, you're telling the scheduler only run them here. And that can help because you can make sure that those host CPUs are not running anything else other than your IO threads. And you're basically dedicating a CPU just to an IO thread. So what this graph shows, the first 4 bars, they are without pinning. The next 4 bars are with pinning. And I tried 1, 2, 4, and 6 IO threads. And what you can see is that with pinning, you get the full performance quicker. And what you can't see here is that when I reran this many times, the no pinning results had more variance. They would change. And that's because with pinning, you just get more reliable results, right? Nothing else is going to interfere, and your IO threads aren't going to be scheduled on different CPUs at inconvenient times. So libvirt has a syntax for doing IO thread pinning. You can just use the IO thread pin tag. The other thing to know about pinning is that the best place to pin is on the same NUMA node where the physical storage adapter is attached, because you might have a machine where certain PCI slots are on a certain NUMA node. So if your guest RAM is there, pin it there with the storage controller, and that's where you get the best performance. So the final thing about pinning is that if you're using multiple hosts, like in a kind of data center scenario where you have live migration and so on, then you really need orchestration or management tool support for the pinning. If you specify pin to CPU number 8, after you do live migration, you don't know what else is running on the migration destination host on CPU number 8, and you might have multiple things running on there, and you're not really dedicating the CPU. So in order to do pinning in that kind of situation, you need support. If you don't, just don't use pinning for that. Performance won't be quite as reliable or as good, but it's still IO thread vert queue mapping still helps even when you don't have pinning enabled. Okay, so I've talked about configuration. Let's have a look at some of the benchmark results. So this is a random read 4 kilobyte FIO benchmark on a local Intel flash drive. And what you can see is that similar to the actual simulation I did in the beginning, we're able to achieve a similar thing. We're able to saturate the disk and get about twice as many IOPS as we had with just one IO thread. So having 4 IO threads is good in this case. So that's nice, but what else do you need to be aware of? Large block sizes. If you have an application that does 64 kilobyte or larger block sizes, you probably won't see the same kind of improvement that we saw with a 4K here. And the reason for that is because you can just send fewer 64K or 256 kilobyte or whatever requests to a drive and saturate it already. So then it's the drive that becomes the bottleneck, and the IO thread, the number of threads you're using doesn't really matter so much. And so maybe even one IO thread will be enough in a case like that. So if that's your workload, then maybe IO thread vert queue mapping isn't very important for you. But if you have a mixed block size workload or a small block size workload, then IO thread vert queue mapping is definitely something to investigate. Okay, another thing I wanted to show you is that the 2x IOPS kind of improvement that I got on my machine is a nice number. But what happens when we run real workloads, bigger workloads, not IO micro benchmarks? My colleague Sanjay Rao at the Red Hat Performance team, he ran HammerDB on Oracle, he ran it on Microsoft SQL Server. And here you can see that when he ran it on 192 vCPU guest. He saw nice improvements, 10 to 20% improvements. But you can already see that as he dials up the workload, the actual improvement decreases. So next, what he tried doing is he tried running 8 instances of the same benchmark on the same host, really packing the host, driving more I/O through it. And then you can see that there's actually the benefits of it go away, and you're basically just in the noise, and there's no benefit. And this is kind of obvious, but the point is that if you have no spare CPU cycles, and if your disks are saturated, this is not going to help you. And the philosophy behind this is that IO thread vert queue mapping, this is not an optimization. It's a feature that allows you to assign more resources to your VM. Okay? So it's not going to make things magically faster. You need to have more resources. If you don't have spare resources to assign to your VM, then your IOPS will stay the same. Okay, so future directions. This is for VirtIO block only at the moment. VirtIO SCSI could also be done, but that will need some more work because the QEMU SCSI layer is currently single-threaded. So all the I/O processing has to happen in one thread, and we would need to refactor that to make it work. Another part of this work that can be reused in the future is the IO thread vert queue mapping syntax and some of the thread setup code that we're using on VirtIO block. If you want to implement multiple IO threads for another device type, say you're doing a user space VirtIO net implementation with multiple queues, and you want to add that to QEMU, today that doesn't exist, it's possible to reuse some of the code. So talk to me, and I'd be happy to chat about some of the things we learned while developing this, and maybe how to do it for other types of devices, non-storage devices. And finally, I just mentioned that this is not an optimization. It's actually just a feature to assign more resources to your Virtual Block device than you could have before. It's still important for us to optimize QEMU, right? There's still all these CPU cycles, this virtualization overhead. And so that's still a good mission, and that's still something that's worth doing. Okay, so to summarize, IO-thread virtue mapping is a Virtual Block feature that improves scalability. It's really designed for IO-intensive workloads. So if you have workloads that have many vCPUs and are driving a lot of IO, you can probably improve your IOPS and reduce the virtualization overhead by trying this out. And I'm also giving this talk here because I also want to let management tool developers and orchestration tool developers know that this feature exists and that you can give this feature to your users if you implement the libvirt syntax or the QEMU syntax that I showed. There's a blog post where you can read more about IO-thread virtue mapping on the Red Hat blog. So check that out if you're interested. All right, thanks.
I want to join the two talks from Kevin and you. Have you tried or thought about using IO threads in QEMU storage daemons so that you can share the IO threads across multiple VMs, and so you can basically saturate the disk across multiple VMs?
Yeah. So in QEMU, so QEMU storage daemon, the QEMU tool that uses the QEMU block layer in a separate process, would allow you to have this architecture very similar to SPDK, where you have one daemon running on your host that's doing all the disk I/O. And those I/O threads could then be shared not just between devices for one guest, but all the devices for all the VMs on the host. So that makes sense if you want to dedicate CPUs, PIN, and everything, those kinds of optimizations. Doing them for every single VM can be hard, but if you consolidate everything into one QEMU storage daemon, then that works well. And it is possible. The exports, so in QEMU storage daemon, the exports we have, like vhost, user block, etc., they do support an IO thread parameter. Right now, it only takes one IO thread. It doesn't do IO thread virtue mapping yet. But this it could be ported now relatively easily to that, I believe. And then we could do that there. So then you could configure your host so that you only have one QEMU storage daemon, say 8 IO threads, and that handles all the IO for all your VMs. Yeah. Yes.
I can. Just two questions quickly. The Oracle database, the HammerDB numbers you were showing, the number of users went up, the performance went down. Do we understand why that happened?
Yeah, I mean, it's the same scenario I was describing before, where if you push your host more, if you're saturating the host anyway, then there's no spare resources anymore. So
CPU in this case, most likely.
Yes.
That's the assumption that we took the CPU away.
Right.
And that's like submission went down, something like that.
Or maybe the disk, maybe the storage system is saturated anyway. You can't push it any further, so the benefit goes down.
Okay. So yeah, so the second question was, I think is general for the community. Like, is anybody using QST? Like, I'm just trying to get a sense, or plan to use QST or anything. Like, are there any users here? I think that's what my question is. I guess not in this room, at least. Thank you.
Yeah, I noticed that you showed the command line for the multi-queue. This is in JSON syntax. Is there any equivalent in the normal form, like k equals the value?
No, no. The answer is it was necessary to only use the JSON syntax because QEMU's command line parsing, the normal command line with non-JSON, can't parse nested structures like this.
Okay.
But I mean, for example, libvirt nowadays it uses JSON, and so I think over time the stack, you know, the JSON syntax is becoming more common. But if you're building your own command lines, you would have to use this. It's not too hard to convert, though.
Okay. Yeah. There's maybe some tools for serialization for this command, passing this command line.
Yeah, yeah. I mean, another thing you can do is libvirt has a feature to dump the QEMU command line. So you could configure it using libvirt and then see, you know, what does libvirt generate, and you can then use that in your own scripts.
Okay, thank you. My second question, I noticed that there's also for Nick, there's also multi-queue. Do you think the idea for your storage multi-queue can also apply for the Nick?
Oh, absolutely. But most of the time, I think VMs nowadays probably use either vhostnet or maybe vhost user net, and they bypass QEMU. QEMU's device emulation, where we implemented all this, is not used at all. So, yeah.
Okay, thank you.
So I want to thank Christian, who's going to ask the next question. He actually wrote a blog post about this before I even had a chance to publish any information about it. I don't know how he figured it out, but thank you. It was great that you benchmarked it, and thanks.
Yeah, so this was actually, we were trying to find out what can we do to improve performance, and some of our research folks basically found that, and so we tested it. And of course, we are also running into issues right now testing things. And one thing that we saw was that the IO thread polling seems to have still some quirkiness. And I think when we look into the IO thread polling again, especially with this multi-queue, there might be more performance to gain, especially for these larger guests with more CPUs or more guests at the same time. Because that is something where we saw turning polling off improved performance, which was unexpected, for example, and other oddities.
Right, right. Yeah, it can, if you turn off polling, then the host will respond less quickly, maybe more I/O batches up, and then you're doing more batching, so less overhead per unit of work. So sometimes being slower actually makes things faster.
So I guess there's optimization potential in that regard.
Yeah. Thank you.
Okay, hi. We are Hannah and Herman. That sounded like a pop band name. So we work in the Vir team in RHEL, and one of the main work that we do there is to maintain virtualFSD. Basically, we want to talk about the line migration state. That is one of the most complex and larger features that we are working on. The qubit integration, and then we will talk a little bit about the performance, some of the issues that we found, and some futures improvement, a new experiment that we are doing for the future. So as I said before, the line migration is one of the largest and most complex features that we are working for almost 2 years now. So currently in Upstream and also in CentOS 9 and Fedora, we support like a basic path-based migration. The good thing is it doesn't require any privilege, but and it's good enough if you have to share like a read-only file system, even if you share with other VMs, or if that file system is exclusively accessed by one single VirtuaFSD instance. And also we are working to support like a more robust file handle-based migration mode. The bad thing is that it requires some privileges, basically be root. And all this work that about the live migration, we started working on this because basically KubeVirt, the idea to share some resources to the VMs and be able to migrate the VM. Currently, if you are using VirtuaFS in a VM in KubeVirt, you cannot migrate. But we found out that also OpenStack will take advantage of the live migration capabilities of VirtuaFSD. So the current situation with KubeVirt, this is like a very schematic, simple architecture of how is a node in KubeVirt. We have like two namespaces, Kubernetes namespaces. It's not related with the Linux namespaces. I hate that everything is called namespaces, but yeah. So currently we have the pod when QEMU runs in its own container that is called the compute container, and VirtuaFSD is run in its own container in the same pod. If you want to share config map secrets, service accounts, and our API, from the people that is not familiar with that is some Kubernetes resources that are exposed to the container as a file system or as a directory with files inside. So it's very normal to use VirtuaFSD to share that file system, that directory with the VM. The current situation is for this type of resources, VirtuaFSD runs unprivileged, and the idea is to use the current path-based live migration to do the migration base. Because these resources are read-only for the point of view of VirtuaFSD. Of course, that can be changed if you update the config maps in the etcd database of Kubernetes, but it changed in a very expected way, let's say. But if you want to share PVCs, let's assume that the PVC is like a shared directory using NFS or any other type of network file system. That's easy to see. The current situation is VirtuaFSD runs as a privileged component, as a privileged container in the same pod that QEMU. And there is kind of problematic. One is the guest can create root-owned files in that PVC, and that's especially problematic if you mix VMs with normal containers workloads in Kubernetes, in OpenShift. And also, in the near future, it's a thing that I think is working from a year now, Kubernetes will forbid privileged containers for the users. You still can have privileged containers in the infrastructure part, like for example, the KubeVirt handler is part of the infrastructure of KubeVirt, but not in the main namespace or any user namespace. I mean the user that use the cluster, no, Linux user namespace. So how can we fix that? Can we make VirtuaFSD non-privileged also for PVCs? Well, yeah, but the problem is it's very rare that one VM wants to have like exclusive access of a shared network file system. That is possible. But the problem is usually the use case is we want to have multiple VMs accessing the same shared file system. So we don't have exclusive access. And also that means that the one VM, while doing migration, other VM can start moving and changing those shared files, like for example, removing it or renaming it. So our current mode that doesn't require any privilege, that is path-based, is not robust enough for all the corner cases that we can have. Especially that, for example, we are migrating, we collect all the paths, and then another VM change those path name to other things. So in the target, in the destination, we cannot find those renamed files. we talk about this in more detail in our last KVM Forum talk. So the link is over there. So basically, we need file handles. But file handles require privileges. So how can we fix that? We cannot make virtualFSD privilege again. So we need to keep virtualFSD as unprivileged inside the pod. So the idea is we are working with Alice, that is someplace, from the KubeVirt team that also works in the Virt team in Red Hat, to implement like a privileged component that will be part of the KubeVirt infrastructure. So it will not be in the main namespace, will be in the KubeVirt namespace that is allowed to have some privileges. This privilege component will be completely stateless, so nothing, there is no state that needs to be migrated, so the migration will continue working. And it will use the seccomp notifier. The seccomp notifier is like an extension of seccomp. Seccomp is like a very generic framework to intercept syscalls, but instead of just simply allow it or forbid that syscall, we have like a user space component, a user space process that usually is more privileged than the one that is monitored. And we can make that privileged component run that syscalls on behalf of the less privileged component. So the idea is when virtualFSD tries to use one of the syscalls that is related with file handles, instead of virtualFSD that all the work, the privileged component will be notified that, hey, this process wants to run this syscall. We will check that that syscall is safe to call, and they will do the calling on behalf of virtualFSD. And then we will return like a signet file handle just to prevent any forgery to the unprivileged virtualFSD. So for the point of view, virtualFSD will work like if he has the privilege enough to work with file handles. This privilege component also in the future can be extended to support also EC Linux and POSIX ACLs, because the extended attributes that are required for EC Linux and POSIX ACLs require also privileges and cannot be namespaced, I mean in the Unix namespace sense. So I think that this could be like a general solution. We think that is the simplest one, even if it doesn't look like. But from the point of view of virtualFSD, it's simple. virtualFSD doesn't require to be changed, and is the part that requires less changes in KubeVirt. And also, since it's a stateless, that will be like a daemon set. If the privilege component dies, will be automatically restarted. So I think it's that the best of both worlds. Okay, this is my part, and now Hannah.
Thank you. Let's talk about performance. So to get a general idea of where we stand with VirtualFS, I wanted to compare it to VirtualBlock. The configuration is that I run FIO as a benchmarking tool on a single file in a file system in a guest. One case VirtualFS, the other case simple file system on a VirtualBlock disk. And in each of these cases, I have 3 different configurations, the first of which is going to use the host page cache to access the backing data on the host. In the second case, we're bypassing the host page cache. In the third case, we don't have any backing data on the host whatsoever, so we have a null configuration. We just immediately reply to every request from the guest as soon as possible, just as Kevin said, to get a look at how fast the interface itself is, basically. These are the results in operations per second. Let's go through each of the configurations one by one. First of all, we have the host page cache case, which is generally the configuration you're probably going to use with VirtualFS. And to my surprise, VirtualFS actually performs just as well as VirtualBlock, basically. I thought it would perform much worse. So it is a welcome surprise, but it's also very boring for this talk. So let's go next to the next case, which is the ODirect case, where we bypass the host page cache. The VirtualFS luckily performs terrible, so I have something to say. I assume that is, or I'm pretty sure that is, because VirtualFS uses completely synchronous I/O internally, so it awaits every single request completely until it fetches the next request from the virt queue. And so the longer the requests take, which happens to be the case with ODirect, the worse it gets. So to fix the performance in this case, we would need to implement proper asynchronous I/O, just like QEMU does it for Verteo block. And in the opposite end of the spectrum, we have the null configuration where we don't await any requests on the host whatsoever. And the first thing you'll probably notice is that there is a big gap for Verteo block between the sequential and the random read case. Now, this is not a Verteo block talk, so I don't need to explore why that is, and can directly focus on Verteo FSD. And I'm just basically assuming that the 470K IO performance for Verteo block is the one to measure against, and you can see that there would be some room for improvement for Verteo FSD in that case. Now, the question is that because of our implementation or because of the interface? And to try to answer this question, I wrote a minimal implementation of Verteo FS just to compare how fast that could be. These are the results. The first two for Verteo block and Verteo FSD are from the previous slide, and now with the minimal example added to it. And you can see, well, performance is basically just as good as Verteo block. So I would assume that the interface itself is fine. Makes also sense because, like, structurally wise, it is very similar to Verteo block. However, it does mean that Verteo FSD has some room for improvement there, so we should really investigate why it doesn't perform as well as this minimal example where we can improve things. Besides that, as I said, we also need to implement proper asynchronous I/O handling for all the cases where you want to bypass the host cache, especially. And then there are some cases where that I did not talk about. So first of all, depending on your workload, you may not be that interested in single file I/O performance, but instead more about general file system performance. Like creating files, listing directory contents, and stuff like that. I didn't gather any data on that, so I can't say anything about this in good faith, so I won't. And leave this to another talk, I suppose. The second case is that when you're trying to use I/O during in the gas for these benchmarks to find performance really suffers. I assume that is because Fuse is trying to use the poll operation, but we don't implement that. I think to implement that properly, we would also need asynchronous I/O support in Verteo FSD. So basically, these two things would then come together, and then we would see whether that improves performance. Finally, the Verteo FS kernel driver supports multi-queue as of this year, but Verteo FSD does not yet. It seems really simple to implement because we already have multi-threading support basically in Verteo FSD. And Rust VMM also makes this really simple. And when I implement this in the very minimal example, I found a 90% improvement for 4Q. So this is also really promising. We just need to do it basically. Moving from quantity to quality, what can we do with Verteo FSD beyond what we currently do? The question might be strange, but let's look at what Verteo FS is to understand why I'm asking it. Verteo FS is basically just the Fuse protocol transported over Verteo, right? Nothing more. So when you're mounting a Verteo FS file system in the guest, what you're really doing is mount just a Fuse file system. Now, for your Fuse file system, it's served by the Fuse kernel driver, which connects to some Fuse driver running in user space usually. And in our case, this Fuse driver is in Verteo FSD, so it's running on the host on a different system. Doesn't really matter. But to communicate, both use the normal Fuse protocol like any other Fuse driver would, except they're communicating through a Verteo FS device, so through vert queues. Now, the first thing we can do, the first fun thing we can do, is to drop that Verteo FS device. So because we just have a normal Fuse driver in Verteo FS, we can just have it connect to the dev Fuse character device like any other Fuse driver would do, and thereby mount the Verteo FS file system, the Verteo FSD served file system on the same host that Verteo FSD is running on. Now that's really, really boring because Verteo FSD ideally is just a pass-through file system. So this would just be a glorified bind mount. But it does raise one interesting question, namely, you can see that for Fuse now we have two different transports, right? So we have either this transport, the legacy transport basically, where you connect to a character device to send Fuse operations through, or you can have the Verteo transport where you transport these operations through vert queues. And the question you might ask, and that certainly can you ask, was which is faster? Kevin already showed a Fuse benchmark. This is another one. So when you write a minimal Fuse, or when I wrote a minimal Fuse server, just to see how fast the dev Fuse character device can perform, I found it's actually not that bad. Can get quite high I/O ops by itself, but actually not as high as Verteo FS. So there seems to be a bit of a gap, at least, between Verteo FS as a transport for views and the dev views character device. So if you were able to use Vertio as a transport instead of the dev views character device, you might be able to gain some performance. And this is specifically what Eugenio thought. And he was asking the question, can you use Vertio transport on the same host, basically just for any normal views file system to improve performance? And yes, you can use that, do that using VDPA and VDUs to connect the VertioFS driver you have on your host kernel to the emulated VertioFS device that's running in user space. Again, for VertioFS, that's very boring, but for other views drivers, it might be interesting. Now, I'm saying VertioFS is very boring, but it does contain a normal views driver, right? So this normal views driver could do anything that any other views driver could do. So why don't we? The first very simple thing where we could start is to transform the file systems we present to the guest. So instead of basically just sending off everything as it comes, we could start simple and make things read-only, or we could transform metadata, like, for example, have a mapping of user IDs and group IDs that differ between host and guest, so that you can have different user IDs and group IDs for certain files in the host, on the host and in the guest. But we can go better, we can do even better and go crazier. For example, we could integrate a network file system driver directly in VertioFSD, that would directly connect to a network, and then VertioFSD could serve this to a guest. The advantage is normally to connect VertioFS to a network file system, you would mount it on the host, and then put VertioFSD on top. By doing this, you save yourself that middleman, basically. You can do other things. You can have an archive file system driver, basically in VertioFSD, so that you connect, so that you can have it open an archive file, and then serve its contents to the guest. Again, the question is why? Because the question is why, and the answer is because normally in this case, what you would do is maybe unpack it and then put VertioFSD on top. But you see that this file system contains a lot of files owned by root, so unpacking it would require root privileges, and putting VertioFSD on top also again would require to run this root, which we don't want. And also, we don't technically need, because it's just a normal archive file, right? So we can just have VertioFSD open it like any other file and serve it to the guest. It doesn't require any privileges, so it shouldn't, right? Now, if I wanted to scam shareholders, which I don't, I would say that we can go even crazier, right? We could have a large language model that generates exactly the file system you want, exactly when you need it, and present it to the guest. So a completely virtual file system. But I don't want to scam shareholders, so I'm giving it back.
Okay, some of the things that we are working currently, that is baking it, so we already have some code upstream, is one is the read-only sharing. Basically, currently the only way to have like a real read-only sharing is to use a bind mount and then share that new mount to the guest. One of the words I really like is the ID mapped mount. The idea is currently that will be very useful for if you run containers inside of a VM. Currently there is some going on in the kernel to support this. So the idea is to have this, the ID mapped mounts, if someone is not familiar, it's like similar to user namespace, but only for file system. The idea is to do just mapping. Also, we are working to improve VirtualFSD to be consumed as a library, as a crate library in Rust. So that could be integrated. Specifically, one of the main use cases is libcurl, that currently is used by Podman. And also there is other people that wants to do that in Cloud Hypervisor and other projects upstream. Also, something that also will be very useful for containers is the reflib support. That the idea is when you copy one file in the same share directly to a different place, it's not really a copy, it's a copy of write. So will be faster. And to make Jan happy, probably in the future we have IOMMU also, and we have more things in the to-do list in the future. So that's what we got. So thank you very much. And if you have any questions.
Thank you for the presentation. I have a question about the live migration. You mentioned that right now it's not so robust in some cases, like renaming a file or something like this happening during the live migration. What would happen actually if that if I were to use the currently released Virtuo FSD, and this case happens? Is the live migration going to fail, or is there a risk of some data loss, or what would be the current behavior? And also, do you expect this to be fully fixed like in the next release, or is it something that will take more time?
Yes, that depends. We have some command lines that you can decide if you want the migration fails, but also we can only detect that in the target. Or you can just mark the say, okay, if the migration finds some error with some of the file that disappeared during the migration, the target, we can say, okay, let's not fail the migration and just communicate to the guest when they try to access that file that file doesn't exist. It will be marked as invalid, like a bad FD or something. So currently you can choose. It's not, I mean, it will work, but the problem is there are a lot of corner cases that it can fail, especially if all these changes happens during the migration. It's happening before and after, there is no problem. With the file handle part, that will be pretty much solved, I will say. And yes, the idea is next release.
So one thing to say is that if we can detect this, we can mark it as an error. Because if a file is replaced, like we might not know. There are things to check it, like you can generate a file handle on the source and the destination, compare these two, and then can be relatively sure that if there is anything going wrong, you will have an error. But this only works if you have the same file system on source and destination.
Hi, thank you for the presentation. I'm curious about the secomp notifier. It's really nice way to, I never use it, to circumvent the privileges issues. How much latency did it add? Is it on the data path or control path?
Well, of course, that will be like a performance penalty. Since we are working and we have like we don't have like a fully working prototype yet. So I'm not sure exactly, because for example, one of the things that didn't implement it yet is all the signature. So we expect that signing the file handle will take lots of time and probably will be the bottleneck of everything. So that we expect that the IIO path, the IIO operations will not be, let's say, penalized by this only when you open a file. So that will be the penalization basically. But the idea is also to put cache and try to improve as much as we.
So just to expand on this idea, just thinking like, I'm assuming that when you open the file that all the requests, like, is it just one-time thing that during live migration, you try to convert your file descriptors to file handles, or just open the file and every time it goes to this privileged component and you get the file handle back?
Well, we can do both, really.
Yeah, but in the current implementation, I'm assuming.
Yeah, well, from my side, I prefer to use file handles always.
Okay.
So it depends on what you're doing, right? You can, using file handles during migration does not have anything to do with whether you're using file handles during the normal operation. You can use either in any combination you want. Probably makes most sense to always use file handles during migration if you can. And then you only have this penalty during migration when you open it on the destination. You can still continue to use them for various reasons, and then you might have some penalty.
Yeah. Yeah. So it'll be, yeah, I don't know. I just wanted to raise this thought, but if it is feasible, if it makes sense, that just convert to file handles only when you need live migration, because that seems to be the primary use case. But there are other benefits to file handles, then doing it all the time kind of makes sense.
You can configure it this way.
Yeah. No.
Yeah,
I can configure it this way already? Yeah. Okay, nice.
Well, you can already use file handles, right, during normal operations, and you can disable that. And so if you disable that and only use it for live migration, then we'll all be converted to normal OPath FDs on destination, and you won't use any file handle during normal operation. So that part is already there, that we don't use file handles.
Thank you.
Thank you.
Hello, everyone. My name is Pankaj Gupta, and I work for AMD in Linux kernel and virtualization group, primarily on confidential computing. And I've been working on Linux kernel and virtualization from last more than 10 years. So today I will present on SNP live migration with guest MemFT and mirror VM. The agenda of my talk, first I will introduce the basic concepts, live migration and primarily SNPs, the approaches which we are taking for SNP live migration. The apparently two approaches, one is the mirror VM and another one is shadow vCPU. Current challenges which we are facing with these approaches, and we'll also talk about the common vendor abstractions and SEV SNP specific tasks which we list on and needs to be worked on. First, I will introduce the AMD SEV SNP, which Tom also explained in detail in yesterday's his talk, and Paulo also touched. So this provides, SNP provides the VM isolation and integrity protection for guest VMs, as VMs will have their own symmetric keys and encrypted with their unique keys, and all the VMs and hosts are encrypted with their corresponding keys. They cannot see the encrypted text of each other. And SNP provides the integrated protection where the guest memory cannot be remapped or replayed or corrupted to avoid these attacks. So this is done with the help of SNP extensions in the hardware and of course the software support. The traditional virtualization used to work is we used to do the emulation in the VMM user space and in the VMM user space, and since with SNP host is considered as untrusted, so it cannot access the VMM memory. So we have to do the emulation, either we have to move the emulation either in the hardware or in the VM address space or VM context itself, so that so for that we also have these hardware extensions which we call as VM privilege levels, and these VM privilege levels provide access protection for the VM memory at various levels, like VMPL0 being the highest privilege level and VMPL3 is the lowest privilege level, and we do the emulation of some of the highest privilege devices on VMPL0, example VTPM, and other privilege operations, example memory acceptance, which is an important step for SNP, which we do at VMPL0 level. And since we for live migration we want a mechanism which can copy the VM memory, and we are also doing the live migration inside guest context at VMPL0. That's the place where SVSM runs. SVSM is a secure VM service module, which is a Rust-based module, which provides all these infrastructure and is developing very fast. And for this, so we plan to use the SVSM to do the live migration packaging and other things. And another important point is this VMPL address sharing or restrictions for address level is restricted by the hardware itself. So in the diagram, you can see SVSM runs at VMPL 0 level, and we have guest OS at VMPL 2, and the normal KVM and QEMU in the host side. SNP live migration, as live migration, we know that moving a running guest from one host to another, it could be same host or another host. But with SNP, we want to maintain the SNP security guarantees while doing the live migration to avoid any of these attacks, which we listed for confidential VM specific to SNP. And since we have no guest memory being only accessed at guest address space, so we want this to be controlled from the guest side. We cannot use the normal vCPU's time to do this live migration, so we need additional vCPUs to do the live migration, because if we steal some time from the normal vCPUs, it will slow down and the effect would be visible. So we need the mechanism which we are going to discuss will require additional vCPUs which run at the guest context and doing the live migration. So these vCPUs will be doing the memory packaging, which is the encryption and hashing together. We'll talk about this. Yeah. For this, two techniques we are considering. First one is the mirror VM technique, and other is the shadow vCPU. And as I said, both these techniques use additional vCPUs, and but the way they create these additional vCPUs is a bit different for both these approaches, and we will see them in coming slides. But only common thing is these additional vCPUs or vCPUs run at VMPL 0 or at the level of where SVSM or Coconut SVSM, which is a current working module, runs. So these vCPUs, additional vCPUs, will not be exposed to guest OS and will only be running at SVSM level. First technique is the mirror VM technique. The mechanism which mirror VM use is it uses a different KVM object and then the primary VM, and it creates these new vCPUs in the context of this KVM object and runs at SVSM layer. Yeah, so it just divides it just reduces the data structures per KVM level, and there's not much sharing on the common data structures like Epic and all these things. And the dirty bit tracking is done at the host side. And yeah, SVSM does the memory packaging, and so only difference is it uses a different KVM object, but it also, this first mirror vCPU is created as the live migration starts, and we currently spawn the mirror vCPU on this mirror VM when we start the live migration from the QEMU process. And if we need more mirror vCPUs, we can spawn it on demand and just to scale the live migration. And these mirror vCPUs are dedicated only for live migration. They go to the guest VM context at SVSM layer, then come back and do the task of packaging and transferring the memory, encrypted memory. So we tried with the mirror VM approach, as this is the feedback we had from the maintainers, and we found out that the mirror VM currently doesn't support the address space sharing between primary and mirror VM. So by address space sharing means right now, sorry, I meant mirror VM with guest memFT. So those guest memFT is a new interface which got added recently in the Linux kernel and KVM space, where earlier we used to, the QEMU process used to have the memory in the user space, address space, but now with guest memFT, the memory is stored in the Linux page cache with direct from KVM interface, file map interface, and there's no involvement of user space doesn't have memory with it, the private memory, I mean. So this is guest memFT, but the current state of guest memFT is it works with the single KVM object. But if we have the primary KVM object and the secondary mirror KVM object, which can simultaneously work on same memory backend, so we don't have that support yet, as it's based on single KVM object. And we need some sort of sharing between both primary VM and mirror VM, because to work on this memory for the mirror VM, and we need some mechanism, like if mirror VM is packaging this memory, like importing or exporting, importing in source and exporting in source and importing in destination. The primary VM would also be working in this memory, so we need different memory view for other operations, like if this memory is faulted on the primary VM or some other operation happened. So this support is not there, and we need we need something like VMA like memory sharing, not exactly VMA, just as we don't have VMAs with guest memFT, but we need some sort of mechanism, example to memory attributes, but with different memory views, example for primary and mirror VM. So there is a patch series. We raised this little bit of this concern with our maintainers upstream, and there's also a patch series present which allows us to access the list of GMEM pages from multiple KVM objects, but this doesn't provide currently the simultaneously or parallel access of the memory from KVM object, or this needs to be tweaked a bit if it gets going. I need to look it more in deeper, and we also had discussions in past few days about KVM Forum for the support of multiple KVM levels, which I suspect needs something similar when we had the discussion with VTL people. And Paulo and Sean had good suggestions how we define those interfaces. So I want something to be added on these things for mirror VM if we go with this approach. So I need inputs on this, how we can make it functional based on what we need currently. So alternate approach which we are considering is we want to we are spawning additional vCPUs which we call shadow vCPUs, and these shadow vCPUs just add into the QEMU address space on the same KVM object, and as you can see the dotted line, they are only visible till VMPL0 SVSM layer. They don't need the multiple, as they share the QEMU address space, and they don't need the multiple KVM handling with guest memFT, and they also can work together on the memory while and do the live migration. So in this case, the primary VM itself does the live migration, and AP creation, the creation method of these vCPUs is done with the dynamic VMSA creation. But this also has, after mirror, I faced problems with mirror VM. I went to this shadow vCPU thing, and we need, and I'm adding these vCPUs dynamically, as there was some suggestions in the past from maintainer, and I added these when we start the migration. So we need some non-overlapping epic ID tied to the current KVM epic object to get it working. So I need to look at that, but apparently this will use the same KVM object. So we are also looking at the common Cocoa live migration problem, and we know multiple vendors need the live migration, and these are the few problems which we are listed and want the vendors to also contribute, as these are common problems. So we in spite of defining our own interfaces, which would not be compatible later with the other vendors, we want to define these vendor APIs or KVM ioctls before. And we had some discussions, but we need to discuss more and involve maintainers. Then the attesting, second one is the attesting the target, where VM, when migrates, it should attest the target itself, so that to make sure where it's migrating is fine. So the important part is integrity protection during live migration, because when we move pages from one host to another, we have to maintain the integrity protection. And this also more or less is a common problem with some vendor-specific bits which can be tweaked later. And guest memFT specific APIs for pre-migration and post-migration also. I see patches on post-copy live migration from James, but I also want these things to be considered based on the approach which we are taking currently, so that later we don't feel we miss something or another. So these are the common interface on which we want more collaboration across the vendors. And lastly, the SNP specific tasks which we plan to work on once we solve the initial spawning additional VCP problem and working on memory migration, memory packaging thing. For live migration, we need a way on which host and the encrypted memory transfers from source to destination. And for that, both source and destination needs to be aware of a common transport key. So we have a mechanism on which we can exchange the keys using attestation from source and destination. Then the memory packaging and dirty bit logging. Host will do the dirty bit logging, and SVSM would package that memory. At the end of live migration, VMSA and other VM state transfer. And important, last but not least, is the end of live migration validation. So all these tasks are big, and they need their own handling. And I want to summarize our approaches which we are taking and where we are currently. So we started with Mirror VM, and with Mirror VM, the good benefit instead, in addition to the having separate structures like Epic for different KVM objects, we also distribute the responsibility to a completely different VM. If in future we have bigger VMs, there's less opportunity of clubber things around, and at least we have a separate object-oriented model. And it also provides a better accounting for cloud providers. And so by default, separates KVM object for vCPUs in Mirror VM, and we don't have to take care of this epic ID problem, which we talked about, shadow vCPU, the overlapping epic ID thing. Both these approaches also have common things which we need to work on, like creating APs. The mechanism is a bit different. The epic ID thing we have to teach to KVM, but the creation of APs from host to SVSM is a common problem we are working on. I worked on the implementation of creation of conversion of QEMU migration threads into the shadowy CPUs by using the host CPU ID based on the suggestion on the last posting, which was around 3 years back on SCV. I have the code, but it's not. I haven't tested it because I can only test once we have the shadow vCPU or mirror vCPUs going, and we want maybe for simplicity we can go ahead with the shadow vCPU thing to get this tested or other things, and parallelly look at the how things evolve for the mirror VM thing, and based on also I expect the suggestions from the maintainers and the community if we go ahead with the mirror VM approach, how we can solve the problems which we are facing currently. Only and the con for shadow vCPU is, as I mentioned, is it will not have a separate KVM object, and all will be in the same context, KVM context. So these are the references which I used and can refer. And yeah, that's it. So I'm thank you for listening. I'm open for questions. Yeah.
Thanks. If I understand correctly, nothing here is really post-copy or LM specific. Are you really just asking how do we implement VMPLs? Because your plan is to do your live migration via an agent in VMPL 0, is that right?
That's right.
Okay, so are you just saying how do we do VMPLs? What is live migration specific here? Yeah, but isn't the mirror VM just VMPL 0?
It's let me yeah, okay. It's another VM which is mirror of parent VM, and it works on the same memory.
Isn't that VMPL 0?
No.
No. Why not? I mean, if your plan is to put an agent in VMPL 0, it can access all of the guest memory. Why doesn't it package the memory and send it across?
So we have to package the memory because if we, yeah, please. Yeah.
It's not the vCPUs. So it's running at VMPL 0, but it's not the actual vCPUs that are doing the migration. It is extra threads that we hoist into the VM in the same ACID so that you can run the vCPUs at the same time that you're shuffling memory over to the destination.
Okay, it's all about running it at the same time.
Yep, yep. And so that's why it's a mirror. It gets shoved in with the same ACID. The code's in there for SCV already in KVM. It just doesn't have to deal with all the other shenanigans.
Okay.
So you only told us half of the story. What happens on the destination? Like, how do you start the VM? How do you attest that you got something that is not hacking your VM? And how do you start with the new VMSA? Because otherwise you break the attestation report of the VM on the original side. Like, of course, I don't expect you to go through it in the answer, but have you thought about what happens on the destination?
Yeah. So when from source, if it's a common encryption key, it will be, of course, after the attestation, when source VM will be starting transfer to destination, it will again need to attest the destination, and if it's a valid host or follows the criteria, and then the encryption key would be known to both host source and destination destination can decrypt the memory which is encrypted by VM, but of course I think the hash key would also be known. But regarding the VM states migration, so we need to at the end of live migration we need to transfer those VM states, vCPU states as well, or VMSA states like VTPM states, and we have to dynamically add those into the memory context. And for that, we either need to slow down the vCPUs, or that's why we need separate memory views, so that it should not be the primary VM working on the memory and we try to do something. So we need to also slow down the primary VM also, and so that we have the entire context created at the destination and get things going. But yeah, it's a good point here.
Yeah, and also regarding what happens on when you create the mirror VM, I'm not sure I understand. When you create, you can only create new VMSAs and before launch finish, right? No, you can only create the BSP before launch finish. So there is no BSP in the mirror VM.
Right, the mirror VM wouldn't have a BSP, right? It's just going to have vCPUs that you would create. The SVSM would call an AP create, and
those do not end up in the measurement. Only the BSP VMSA ends up in the measurement.
Right.
So you would
with an SVSM, yeah, it would just be the BSP VMSA that's in there, and then all the other vCPUs are created by the SVSM. So you're trusting.
So basically, you have to kind of fake starting the VM with launch finish on the destination, so that you get a measurement that's valid, but then you cheat and overwrite memory behind the VM's back with data that is, of course, encrypted with all the proper protocols to ensure that it's secure behind the back of the VM on the destination, so that it can actually start. And then you basically at some point tell the SVSM, do not start normally, overwrite your VMSA with this new thing and start with this new state. Some kind of trampoline or something.
Yeah, there's also a concept in the architecture of an IMI, an initial migration image, which is a subset of the initial launch image. So you can launch, you want to launch the same thing on the destination because you want to have the same identity associated with it. And so you could either launch the exact same image that you initially measured, or you can launch a subset of it, just the pages that are marked as IMI pages, and that's still good enough.
And I think that this IMI thing may also be helpful with what Ani, Alex, and Vitaly were presenting yesterday, because then you have something that is much smaller and much less likely to have issues with the customers wanting to bring its own migration image or something like that.
So this week we've had a few questions about a network connection from the SVSM. It's been talked about for the VTPM provisioning, for instance, and this idea of, do we want a TCP/IP stack inside of the SVSM, or do we want some sort of proxy going on? So I guess my question for you is, for live migration, have you thought about what the actual mechanism for getting the pages from the source to the target would be? And is there some overlap there? Would it be going more towards QEMUs, through QEMU's existing migration flow, or would there be sort of more like an independent networking connection happening inside of the guest? Maybe there's some connection between these two different needs.
Yeah, sure. Right now, I don't see like we should have the TCP IP stack in SVSM, and how we see it is we put the packaged memory from the QEMU source to destination in the output network connection. Maybe it's, again, I don't know whether it will be TLS or something, but it's through QEMU network connection with the destination. But the memory is packaged, and we need some mechanism with which we make sure whatever is sent, of course, if it's hashed, hash should be measured in the checked in the destination, but we need to see the sequencing, or there is anything happened, abrupt thing happened in the communication with some sequencing or something. Yeah. So this is.
So I think all that is needed is some pre-shared secret for the source and destination, or an asymmetric key, where the source just, so the source just encrypts everything, and then we let QEMU do its thing, transfer the memory as usual today, and then the destination knows how to decrypt it, so plug it back in. So SVSM itself does not need to do that.
So do you need some private and public key for?
Correct. Yeah.
So it will not be public-private key. It will be a secret key, transport key.
Just on the guest MemFD, if we're going to go a KVM VM per VMPL, then it totally makes sense that we need to get guest MemFD to be able to be used by multiple KVM VMs.
Yeah.
So I think that's probably the way to go. Yeah.
Yeah. Yeah. Thank you for listening.
Hello, everyone. We're going to spend the next 30 minutes discussing VSM and how we're planning on emulating it in QEMU and KVM. My name is Nicolas Sainz. I'm a hypervisor and KVM engineer at AWS. We build a Nitro hypervisor, which is the hypervisor that powers EC2. So it's a mix of KVM and a proprietary user space. And yeah, every time you launch an instance through EC2, it goes through Nitro. The talk is going to be a mix of me re-explaining what VSM is and why we want VSM. And then I'm going to discuss how we managed to get all these integrated within QEMU and KVM. The ideas that were great, and probably the next steps and how all this is going to eventually pan out into a common framework for VMPLs, TDX, and VSM. So VSM is a bit different than other confidential computer features. There's a different security promise here. So although some concepts are similar, the end result is very different. The idea is called virtualization-based security. And what we want to do is protect the guest against itself. So if at some point your guest gets compromised, we might be able to leverage the hypervisor to harden it. So this is your typical hypervisor stack. We generally sit in that red boundary. VMs have absolutely no visibility in what the host is doing. They cannot really introspect. But on the other hand, the hypervisor has full visualization on what's happening in the VM. That creates, on non-confidential computing workloads, a necessity for VMs to trust their hypervisor. In more formal parlance, I think that means the hypervisor belongs to the trusted computing base. That's something we can leverage to harden the guest. Just to give you a high-level example, once a VM is running, it might have a set of secrets, and by secrets I mean pretty much anything, binaries, data, photos, whatever, CPU state as well, and some policy that decides who gets to access those secrets. Again, very broad, read-write memory access to a file, or whatever framework the operating system uses to control access to secrets. And within that context, it's very possible for an attacker that has gotten control over the operating system to disable the policy and access those secrets. That's what virtualization security might be able to protect and avoid by moving both the secrets and the policy down into the hypervisor. Okay, it is very abstract, so I'll give you a little example so at least you get an idea where I'm coming from. Again, a secret in memory, some read-only memory that the VM wants to remain as such. An attacker gets kernel access and manages to update the page tables, so now it's able to modify the memory. And that's it, you're compromised. But one thing the VM could do, if the hypervisor was enlightened to do so, and the VM as well, it could request the hypervisor to ensure that that memory is read-only. And not only that, it could also attach some policy to that promise. So whenever this attack happens again, the hypervisor can stop it, and through that policy that was attached to the read-only request, inform the VM of what happened and allow the VM to introspect itself and realize what was happening. Of course, in the whole process, the memory will remain read-only, which is very nice. It's not only about memory. The hypervisor has full control over the system, so we couldn't introspect pretty much on every aspect of the virtual machine lifetime. Okay, in comes VSM. So VSM is a way of, it's a framework that allows virtual machines to do this. It was introduced by Microsoft. It's a spec, so it's commonly known as the TLFS. And there's nothing really Microsoft specific within that spec. So there's nothing preventing us from implementing this one-to-one in QEMU and KVM. And also, there's nothing preventing Linux guests from using all this framework. So it's fairly flexible. For now, it's only x86 specific, but there's work going towards ARM64 as well. But we won't know much about it until they publish the spec. But as far as I've heard, the hypercall spec is going to be very similar. So all I'm going to explain now, it's going to map to ARM64 as well. One of the core concepts VSM introduces is a concept of virtual trust levels. And again, this is going to be very similar to VMPLs, which we've been discussing in the past. A virtual trust level is an execution context the CPU might be in. And CPUs now have multiple of those execution contexts. Those VTLs are hierarchical, so we consider VTL1 to be more privileged than VTL0, and so on and so forth. There's only 2 here, but we can go all the way to 16. The hypervisor is the one that does the work of switching from one VTL to the other. And when it does so, it saves the state of the dormant VTL, and it's the one that knows how to do those state transitions. There's 2 hypercalls to do that, VTL call and VTL return, and the semantics of how all that works, it's explained in the TLFS. The most important thing here is that each VTL has some private state that, again, the hypervisor has to save, and it also has shared state that it has to mirror on VTL transitions. VTL return, again, as long as VTL1 is running, VTL0 is not allowed to preempt VTL1 because it's higher priority context. And it's going to run as long as VTL1 doesn't explicitly do a VTL return, which goes back into the least privilege trust level. Every VTL also has hierarchy controllers, so they can IPI each other. There's timers as well, so VTL1 can set up a timer, go back to VTL0, and eventually when that timer fires, the hypervisor is tasked to do all the switch. These adds some complexity in the implementation because interrupt routing has to be VTL aware, and we'll see in in the next slides how we solve that. VTL also introduces hypercalls to control who gets to see which parts of the memory. So VTL1 can decide to hide some memory from VTL0, or VTL0 can request VTL1 to map memory regions with specific permissions, again, to hide secrets or to protect secrets. The VTL1 also can log the CPU state in unprivileged VTLs. Again, some registers in the CPU, once the operating system is running, won't really change. So it's very interesting in terms of security. And of course, VTL1 has full visibility over the CPU state of lower privileged VTLs. Each one of these functionalities is a set of hypercalls. I'm not going to go through them because the list is long, but we've managed to implement all of them or parts of them that we cared about with what I'm going to present next. One last thing VSM introduces that's very important, and that goes back to what I was talking about policy. Whenever one of those promises is broken, be it VTL0 trying to access VTL1 memory or some register changing when it shouldn't, VSM introduces the concept of secure intercepts, and it's a way the hypervisor has to inform a privileged VTL that something wrong happened in unprivileged contexts. And yeah, and that's how VTL1 is going to be able to react to all these events. You might be thinking, what about I/O? DMA could just go and access all that memory. Again, it's up to the hypervisor to fix that. All DMA happens in VTL0. That's what the spec says. And it's up to the hypervisor implementation to make sure the IO-MMU page tables match VTL0's permissions. I'm not going to go into this topic more because it's more an IO-MMUFD problem, but we're working also towards that direction on how to implement that efficiently in QEMU and KVM. Well, in QEMU. So now your virtualization stack looks like this. Within your VM, you're running your normal, what we call the normal world, which is just your operating system, and you have a sidecar operating system. Generally, it can be anything really, but you'll want a very small operating system that's capable of doing all these operations that I described: locking memory, locking register state, maybe introspecting into the normal world and making sure some structures that are critical haven't changed or have changed in specific ways. There's a lot that can happen there. It's also a nice place to hide keys, for example. And that's something that Microsoft does. It's called Credential Guard. So I want to go back to the previous example I gave, where we want to hide some read-only memory. And normal world gets compromised. The attacker gets to update the VM's page tables. But in this case, well, the access is not going to come through because the hypervisor intercepts it. The hypervisor then issues a VTL switch, injects a secure intercept, a memory security intercept, stating that some CPU did a bad move, and that's it. The secure world gets to introspect into what's been happening, and in any case avoids any of that attack. So where can I use this? Right now, this is only available, as far as the guest is concerned, in Windows. It's pretty transparent. You can use it. You just click some configuration option, Credential Guard, and it will be enabled. In terms of hypervisor, you can use Hyper-V, but you can also use EC2, which supports all these features. And that's for production quality usage. There's some research being done to get Linux to do all this in the guest. And of course, what I'm presenting here is how we've implemented all this in QEMU and KVM. So how do you emulate this in QEMU and KVM? This is the responsibility split when we presented our intention of upstreaming all this last year in KVM Forum. everything was very KVM-centric. We added VTL awareness to pretty much every single KVM structure, so vCPUs, VM, memory management, APIC, and it didn't work well. It adds a lot of complexity across the board. Especially the APIC part was very, very hard because now you have to enlighten KVM to be able to route interrupts across VTLs and understand who has which priority and so on. And it was very implementation specific for an extremely generic code base. So we had some discussions, and of course we all agreed that it should move upwards into the hypervisor. And I'll now explain a little bit of how we managed to get that done. So this is your VSM VM. The first thing, well, before I continue with this, I want to say something. Since LPC and KVM Forum, we've been sitting down with KVM maintainers, AMD, and other people that are interested in doing this execution concept in QEMU and KVM. And we've come up with new ideas that we haven't yet implemented that are going to vary a little from what I'm presenting here. It's okay, because the outcome of our conversations matches the overall design I'm presenting here. But keep in mind that the end result is going to be slightly different. So yeah, if QEMU wants to launch VSM VM, what it first does, and I'm simplifying things, it creates two distinct KVM VMs. It now has to track two KVM states, which is a challenge on itself because KVM state is kept as a global variable across the board in QEMU. But it does so because it adds a very nice implicit namespacing for APIC and memory management. And we'll see how we use that implicit namespacing to really model VTLs properly. It also creates a vCPU for each KVM VM. So for the case where we have two VTLs, we'll double the number of vCPUs. Again, it's a very good container to keep track of all the state of all the vCPUs, of all the VTLs. It works very well in that sense, although it's a bit, it adds a lot of overhead. It also allows us to track, to target specific VTL vCPUs in a very convenient way without having to introduce VTL awareness in the kernel. We were forced to introduce the concept in QEMU of CPU namespaces because QEMU uses the APIC ID to query CPUs when it's looking for a specific CPU. That doesn't work anymore because both VTLs share the same APIC ID. So what we did is create a concept of namespace, and a CPU has both, it's a pair, like APIC ID and namespace, which you can pretty much choose whatever you want. That allows us to query specific vCPUs across QEMU. And that's important because we also had to introduce a VTL scheduler. And it's a little state machine that takes care of doing all the scheduling of the two VTL vCPUs as well as passing the state across them. You can see how I've named differently the VTL0 CPU in QEMU versus the VTL1 CPU in QEMU. And that's because an area we want to eventually research is whether we really need a full-blown x86 CPU model for VTL1. There's only so much VTL1 is allowed to do, so I think it's very likely that for the production quality version of this, we'll have to create a specific CPU model for VTLs. We'll see. I can't hear you, sorry.
I just wanted to ask if with the design that we worked on yesterday, will the VTL scheduler still exist?
It can exist. Nothing prevents you from doing one. As long as you don't accelerate through the new design, you still need to do some scheduling. Depends on the fine detail of how we do. Because
So
you're allowed to do the switch outside of KVM with the new design.
In that case, you have 2n threads, right?
2n?
Threads.
Yes.
Okay, so instead with what we talked about yesterday, you have n threads. So you have the VTL scheduler code, but not a full-blown thread scheduler, right?
Yes, yes. And again, these might change once we get the final design, but the ideas are going to be somewhat in the same area. Again, well, it's a discussion in progress, so I can only do so much in that sense. Now, how we solve the problem of having different memory mappings for each VTL. This is, I think, something Sean proposed. And we're using memory attributes. Since we have namespaced KVM VMs, we can target specific VTLs. And memory attributes, which are not upstream, but we sent a patch series already, and we're working on a second one, allow you to switch the permission bits on specific guest page addresses. So now we get per VTL protection, but we also have memory fault exits. So this is just a mechanism that KVM has to inform user space that one of those memory attributes was breached. And it allows user space to then do all the VTL dance to inject a memory intercept. And the last thing we've had to introduce that's like a new change to KVM, it's event polling. So as I mentioned earlier, VTL1's interrupts have precedence over VTL0's execution. So while VTL0 is executing, we need to make sure that VTL1 hasn't pending interrupts. And whenever we get an interrupt, well, we set up a system where KVM sleeps for you within KVM and monitors for interrupts through your regular APIs. And and you get an exit whenever you have a pending interrupt. It allows, again, the VTL1 thread to do the switch and scheduling VTL1. So this is a quick slide just to show how the different KVM VMs isolate fairly well the memory configuration of each VTL, and that's one of the most important things for our design, and the one that was more complex to solve. And I'm going to show you a very abstracted way, a very abstracted picture of how a VTL switch happens now with this new setup. This is the steady state of any virtual machine where VTL0 is running because it's the normal operating system, and VTL1 is just polling for events because it has nothing to do. And eventually, VTL1 had set up a timer, so event polling comes back into user space and notifies the VTL1 thread that, hey, I have a timer. There's some little back and forth with the VTL scheduler that takes care of kicking the VTL0 CPU out, synchronizing the state of VTL0, passing the shared part of the state to VTL1. This is something we don't like at all because it's very expensive to do. And then schedules VTL1. And, well, it might want to poll VTL0, might not. It's not very important. There's a special feature to avoid latency in VTL0 that we can implement. And that's why we want event polling in VTL0. Otherwise, we just sleep until VTL1 returns. This is the final responsibility split. Again, we're happy that VTL awareness is completely out of KVM. And we've been able to introduce low-level primitives within KVM that are most likely useful to other use cases. I haven't talked about all of them, but I think the most important one are event polling and memory attributes. We have some, of course, all these are work in progress, so please don't assume this is ready for usage upstream. But I'll be interested if anyone needs any of these features I'll be interested in hearing about it and maybe converging on a design that works for everyone. Upstream status, well, those at the top are available as upstream series or are about to be available because we're going to send them this week. Upcoming RFCs, we're working on CPU register filtering, just a broad idea of how we would like to do it, and we'll send it as an RFC and we can start the discussion. And maybe in the future we want to do MBEC-aware memory attributes. As for the upcoming QEMU RFC, I had some ideas there, but I just deleted them because after our discussion with AMD, Paolo, and other interested people, we're going to have to figure out the design. So it's a question mark. Where can I run QEMU and KVM? A VSM with QEMU and KVM? Well, right now you just have to go to our repos, and it's a very proof of concept-y build. So don't expect anything production quality. So I would just use it to research as a research project. But in the future, it'll slowly become a more serious production thing. VSM on Linux guests. This is coming up next year, where we're collaborating with people from Microsoft and want to build a full open source VSM stack. So the idea is to be able to run a Linux guest plus our code in QEMU and KVM and implement all these security features in an open way. Microsoft also announced that they are now using VTL2 and that they moved all their VMM into all their VMM process and device simulation into VTL2. And this is exciting in a way because it's a new paradigm in terms of how we design hypervisors. But it's also a problem with all the design I've been showing you so far, because this requires way more performance than what we can give at the moment. Our current design is very slow, but it's fine for virtualization-based security because once everything is set up, you don't ever go into VTL1, which is what we want. But once this becomes a reality, and if you want to use this in the Linux world, maybe we have to rethink how to accelerate VSM. And that's where the new design that it's a question mark comes. That's it. Thanks. I'm open to any questions or comments.
Thanks, Nicholas. Are we going to need to have IOMMU FD memory attributes similar to what we have in KVM, or will IOMMU use the same ones as KVM, or what's going to happen there?
There's not a clear plan on the API itself, but what Jason is working on is implementing the core page table modification operations to be able to do this in an efficient way. That is, cutting a huge page into smaller pages, modifying attributes on specific pages, all atomically while DMA is happening in parallel. So Jason is working on a framework for that. Once we have that, we're going to think about how we connect the two.
Yeah, I wouldn't expect it to be as complex as KVM because you only have to deal with VTL0. So you don't need multiple mappings. And I'm guessing you probably can't execute. So you just really need to say, be able to say read only, because writable you can do by just punching a hole. So I expect it would be quite simple compared to KVM's mess.
There's also no access.
Right, but you can always just, I assume you can unmap.
Yeah, you can.
Like
but the problem is how you map in a way that doesn't break DMA.
Yeah. Very random. Can we kill off read-only memory in QEMU and KVM for VSM guests to avoid the further complication where you hit a read-only mem slot that is writable but not readable in the attributes? Just something goofy like that.
You want to disable the option of read-only memory slots just to avoid the...
Yep. That's probably a follow-up question.
There's no write-only memory attributes, I think. No, you cannot do it, I think.
I think what? Okay, so it's because it would cause an APT misconfig. So I think it fails.
Like the PTs won't allow you to express that.
I think that the hypercode would fail.
Sorry, ignore the right thing. A GPA that has a read-only mem slot but is not readable per the memory attributes because then KVM's existing ABI is that you emulate and trigger emulated MMIO, but it's not readable. So are you supposed to inject default? Or are you supposed to exit to user space? Like, can we just avoid that whole thing and say you don't get option ROMs?
XW permissions are illegal. You have exec only, but not exec wide.
Right, but I'm saying where the memory attributes for the VTL says you get nothing, complete access disabled, but the mem slot is read only. Then you have to define semantics for which one wins. But can we just kill that off and not deal with it?
So I'm saying it's not hard to define the semantics. We need to see how hard it is to implement them, because the obvious semantics is that the memory attributes win and you cannot access them at all. It always causes an intercept. Then if it turns out to be a pain in the back to implement, then we decide whether to kill it off.
Wait. No more questions? Oh, we're done. Okay, sorry. Thank you very much.
Hello everyone, welcome to my talk. My name is Melody Wang. I'm a member of AMD APEC Linux Kernel Enablement Group. I'm working on secure virtualization. Today I'm going to talk about secure interrupt delivery for SEV SMP guest. First, I will give an introduction about what the problem is, and then what the solutions are. Then I will talk about one solution, alternating injection. Basically, what the alternating injection is and what we need to be done there. So, why is a secure interrupt delivery needed? The answer is the hypervisor is untrusted, but it's in control of interrupt injected. The malicious hypervisor can decide when and where to inject the interrupt. Sorry. Well, if the guest is not ready for handle the interrupt, its execution could be compromised. There are already some attack examples. Take one example. The malicious hypervisor can inject the interrupt 29 at any point in time. It can trigger the PON-VC handler and control the value in the exit reason register. These are very powerful primitives for the attack. So it can break the confidentiality and the integrity of the guest. We can see the problem is pretty severe. So to prevent the attack from happening, we need a more restricted interface between virtual machine and the hypervisor regarding the interrupts. So the virtual machine can selectively accept or drop the interrupt. In other words, the guest is in the control of the interrupt delivery. Therefore, it can protect themselves. So between the interface of untrusted hypervisor and the SMP guest, there are three protect solutions: restrict injection, alternate injection, and secure AVIC. those are all hardware support features the SMP guest can use. Restrict injection disable the interface interrupt queuing and the injection interface, while the alternate injection it still keeps the standard virtual interrupt queuing and the interface, but it's controlled by the guest itself. The secure AVIC is advanced virtual interrupt controller. It is a hardware acceleration. Among those three protection solutions, restrict injection and alternate injection already supported in the current hardware. The secure AVIC will come in a future part. Before we move forward, let's take a look at the difference between restrict injection and alternate injection. So restrict injection have a better performance than alternate injection. The reason is there's no virtual machine privilege level transition. However, it's not preferred for a Linux guest. It's facing obstacle upstreaming. The reason is x86 exception handling. More specifically, the nested exception detection is problematic. So we have a concern about the nested PON-HV detection is not reliable. So we switch to alternate injection. In alternate injection, the restrict injection is used to inject into a secure VM service module. So it requires VMPR transition. However, it doesn't have the concern related to the restrict injection has above. The reason is SVSM is simpler. It can handle nested exception properly. So we focus on alternate injection. Next, I'm going to talk about what alternate injection is and what is need to be done there. Let's take an overview about alternate injection. So the hypervisor gonna use the restrict injection to inject the interrupt into the SVSM. By using restrict injection, we can protect the SVSM from the malicious interrupt. Therefore, leave the guest OS safe. SVSM is running at VMPR DISO. It is a trusted entity. So the SVSM will do the, sorry about that. The SVSM will use alternate injection to present the interrupt to the lower VMPRs by writing to their VMSA. To support this scheme, the following is what we need to do. So first, we need KVM support for restrict injection into the VMPR DISO only guest. In the traditional injections, the general interrupt, NMI, and the machine check, they will be injected into the guest OS directly. With the restrict injection, of course, first we need to enable restrict injection, which include hardware support and the guest request. We are going to disable all of the interrupt, all of the hypervisor-based interrupt queue and the interrupt interface. Instead, we will have a new exception vector, PON-HV. All of the general interrupt, NMI, and the machine check will only be able to inject with the PON-HV. And the interrupt have to go through a trusted filter. It's controlled by the virtual machine itself. Besides that, we also need a KVM support for GCB restrict injection non-automatic exit events. There are PON-HV doorbell page, which will register a doorbell page with PON-HV for communication between hypervisor and the guest. There's also a PON-HV API if you needed to send the API around those vCPUs. Also, there is a new require feature for restrict injection timer. If you request timer support from the hypervisor when the restrict injection is enabled. Next, let's talk about what we need to be done for KVM to support the alternate injection. Let's take a look at the alternate injection flow, then see what we need to be done there. So when we need to inject interrupt for VMPR1, of course, with the alternate injection, of course, we need to enable the alternate injection in hypervisor, which also include hardware support and the guest request. Also, the KVM need to support to inject the interrupt to the different VMPR levels. It inject interrupt into the SVSM with the PON-HV first. Then the SVSM will do alternate injection by going through SVSM APAC emulation. Then write the interrupt to the AMSA of the VMPR1. Afterwards, request to switch back to VMPR1. So the hypervisor gonna run VMPR1 and start to handle the interrupt. Here comes a kind of a key questions point, like why SVSM can do the alternate injection instead of a hypervisor. The reason is SVSM is running at VMPR1, and it can write the guest private memory, which is a VMSA. So that's the main reason about that. Besides that, there are proposed changes to the GCCB to support the alternate injection. There are two parts. One is the changes to GCB NAE events. One, we need to configure injection notification vector, which will be used by the hypervisor to notify the SVSM about interrupt injection processing. Disable alternate injection. It requests the hypervisor to disable alternate injection for a specific VMPR when this VMPR doesn't support alternate injection. PON-HV timer. We need to extend the PON-HV timer for the timer interrupt for a lower VMPR. There's also a specific EOI for a level sensitive interrupt. It will avoid the risk condition when the hypervisor is processing a new level sensitive interrupt request, while the SVSM is still working on complete EOI for a lower priority sensitive interrupt. And we also need to have extended interrupt information for multi-VMPRs. Now, let's take a look at what needs to be done for the SSM itself. So the hypervisor, as we talked, it needs to use the restrict injection to inject interrupt into the SVSM. So the SVSM first, it needs to enable restrict injection. Also, it has to be able to handle the PON-HV exception. Then we also need the APAC emulation, which we'll use to present the interrupt to the lower VMPRs. Also, the APAC emulation will protect the guest state in the guest itself from leaking to the hypervisor. Besides that, We also need the SVSM APAC protocol. It's used for the lower VMPLs to configure its APAC state through the SVSM. Before we move to the next slides, I want to talk about traditional APAC protocol. So we have this in mind, then we move to the next. So traditional APAC protocol are using KVM APAC emulation. When the guest needs to modify its local APAC register, it will send a request to the hypervisor. The hypervisor gonna use the KVM APAC emulation to handle this request. Obviously, we can see all of the sensitive information will be leaked to the hypervisor. That's why I want to have this in mind, so we can move to the next. So next is what we need to do for the Linux guest to support alternating injection. So let's take a look at SVSM APAC protocol flow. When the guest need SVSM APAC request, it will prepare the SVSM APAC request. It involved written to the SVSM calling area. After it's done, it's gonna request to switch to the VMPR ZISO, which is the SVSM. The SVSM gonna process this SVSM APAC request, then switch back to VMPR1. The VMPR1 gonna process SVSM APAC result. From what we can see, obviously, the hypervisor is only responsible for the VMPR switch. So there's no sensitive information will be leaked to the hypervisor. So simply, what we need to do for the guest is we just need to enable the alternate injection for the guest and inlet the guest for the SVSM APAC protocol. So for alternating injection for the guest, there are two parts. Firmware and the guest OS have a separate enablement. Worth to note, those are only the changes that need to be done in the guest. So let's summarize what we are right now. So for KVM support for restrict injection into the VMPR ZISO only guest, we have sent the patches upstream for review, and the patches support for most of the GHCB requirements. The PON-HV API and non-EUI required is still under development now. As to KVM support for alternating injection, the SVSM hypervisor support is multiple VMPR support. It's still under development. There's a talk about that yesterday from my colleague, Tom Lantaki, and also Jörg and Rory from SUSE. They have a talk from that too. I mean, if you are interested, it's worth your time to watch their recordings. So after that, then we need to work with the multi-VMPR support to track a separate site interrupt source for each VMPR. Then for Linux guest support for alternate injection, it's under development right now. The last is the SVSM support, restrict injection for VMPR ZISO, APAC emulation, and SVSM APAC protocol. Most of them code are already pushed in the Coconut SSM by John Line from Microsoft. The restrict injection for lower VMPRs, it will be done in the future. These are some reference link if you are interested. Okay. Thank you. I'm open for questions.
So I don't fully understand the. Thanks a lot. Amazing presentation so far.
Thank you.
I don't understand the problems with restricted injections. I heard that the upstream conversations went south and everything was bad, but I don't understand the technical reason why an SVSM is able to serve an HV in a reentrant way, but Linux can't, and whether alternate injection actually solves a completely separate problem from the nesting, because it also pulls LAPIC emulation into the guest, which then has completely different additional side effects. So what exactly is the real problem with restricted injection?
Are you talking about a restriction, the problem in Linux guest directly?
Yes.
So I think it's the legacy problem in the x86. I think it's about the stack transition. So they have the problem with detect the nested exceptions. But in SVSM, it's much simpler.
Why?
I mean, it doesn't have the legacy problem because I think Europe probably can help answer that question.
An HV, thank you, Jörg.
So the problem is the HV exception, which can come at any time. You cannot block it. It can even come while the HV handler is running. So the HV handler must be IST, and when you get another HV while the IST handler is running on the IST stack, you're basically screwed, right? So, and the Linux entry code is already not easy, let's say. It's actually pretty complicated. And the upstream maintainers were not keen to complicate it anymore with another NMI-like exception type like HV.
So the HV handler overrides the stack pointer, right? If it's a normal interrupt.
So Coconut does not have to use the IST for a bunch of the vectors that Linux does. Linux uses the IST for anything that can happen in the syscall gap, right? So NMI, machine check, DB, so on. And because those can nest, it makes the detection of whether you already had an HV harder. I think we had some patches for that. I think, was it Peter Z who didn't like them? But Coconut doesn't have all those other things because it doesn't have a syscall gap. So it doesn't have to use the IST. I mean, it doesn't use syscall at all, right? So it doesn't have to use the IST for, I think, anything other than double fault, right?
Based on the experience, the discussion which we had with Peter Z, we tried to convince the little bit handling of nested exceptions, which already was there with NMI and VC existing similar for HV, but he said that if you add more things, it will be harder to later find out if it clobbers the syscall gap later. So it's not a one solution. So the solution was the Fred later. So that's what he suggested. But I think secure awake doesn't. The
question is, will secure awake solve it?
Yeah, it will solve because I think that it doesn't give the HV point HV. It does whatever handling is done with VC little bit, and there's no IST nested IST exceptions for secure awake.
Okay, so once we have a secure AVIC, there's no need for an alternate injection. We can just simply pass in a secure AVIC and everything is good.
Yeah.
Well, that's almost true, but unenlightened guests that want interrupt protections would have to run with alternate because that's the only way you can fully emulate an APIC.
I think we had the conversation multiple times over this event. I don't think that confidential computing and unenlightened guests are a sensible combination. So we can just assume that with a secure AVIC world, we will have the ability to not have the alternate. It's just a lot of overhead, right? Like jumping back and forth between VMPLs, all of that is software switching, is just slow and tedious. And it also pulls in another emulator into my TCB, which I really don't want to have, yada, 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 right?
I hear you, but that there's more opinions to that. Sorry.
You might not like the more opinions. My question was going to be the same from an upstream perspective, like ignoring CSPs or downstream people that want to take on the tech debt of this. From an upstream perspective, why shouldn't our stance be give us secure AVIC?
Well, we have 2 generations of hardware that are out currently that don't support it.
Which is a good argument for the CSPs and the downstream people, but from an upstream perspective, what's there that makes it worth supporting for 2 generations?
Lots of people who have hardware that they would like to use.
So I have a question that's more also on the Coconut HV thing. What makes Coconut not have a syscall gap, since Coconut also has user space?
Syscall just uses Coconut just uses int 80 as the syscall entry point. It does not use syscall right now, and we also don't use it for swap.js because we don't use JS in the kernel. For pure CPU, we have pure CPU page tables where the pure CPU area is actually mapped at a fixed position, so we don't need JS as well. So that's why we don't need IST for anything but double fault. So yeah. It's not performance. The question was whether it's for performance reasons. No, it's actually for keeping things simple. So yeah. Right.
Thanks, first of all, to Melody, even though the conversation was a bit between the audience, but thank you again. We're going to have the group photo now, and I think the best place is probably downstairs, outdoors of the restaurant. So let's meet there in a few minutes while the other room finishes.
Thank you.
Let's get started. Hello, everyone. I'm Chen Yan Lin from National Taiwan University, and I'm here to talk about our work, which is about virtualizing ultrasound on KVM QEMU architecture and setting up an APT VM based on our virtualized ultrasound environment. Here is the outline of my presentation. I'll start with a brief introduction to ultrasound and APT. Next, I'll talk about the motivation and the main objectives of our work. And following that, I'll introduce the design of our approach, where I'll dive into the technical details of how we adapted KVM to support our virtualization model. And I'll walk you through the modifications we made to APT to integrate it into our virtualized environment. After that, I'll present the evaluation of our approach. I'll share the execution time of our virtualization model on different APT applications. Finally, I'll discuss some of the future work we are currently planning. Before we dive into the details of our work, let's start with a brief introduction to ultrasound. The key concept of ultrasound is word isolation. Ultrasound splits the processor into two distinct words, the normal words, where the general applications and operating systems run, and the secure world, which handles sensitive operations like encryption, secure storage, and key management. This isolation between words ensures that even if the normal world is compromised, the secure world remains unaffected, providing a robust layer of security. To manage the word switching, ultrasound relies on the secure monitor in EL3. When an application in the normal world needs to interact with a trusted application in the secure world, the CPU will generate a secure monitor code to trap to EL3. Then secure monitor in EL3 then performs the word switch to prepare the context for the secure word. Then the CPU can enter the secure word by generate another exception return and enter the secure word and execute the corresponding trusted applications. However, ultrasound only provides hardware isolation. It typically needs a secure operating system running in secure EL1 to provide software management. This secure OS manages the execution of trusted applications and ensures secure operations within the secure world. The most common secure OS is APT, which is the target we try to run on our virtualized ultrasound. APT is a widely used open source framework that provides a trusted execution environment known as T, based on ultrasound. One of the key advantages of APT is that it allows developers to implement trusted applications within the secure world. Trusted applications are usually used to handle sensitive operations and are protected from the normal world. And as I previously said, when a CPU needs to switch to a secure world, it generates a SNC to trap to EL3. Then the secure monitor, which is the firmware of APT, then handles the SNC and switches to the secure world. Once the CPU context is switched to the secure world, the APT OS takes over and invokes the appropriate trusted applications. Once the trusted application is executed and complete, the result is passed back to the normal world through the send SNC mechanism, ensuring that the separation between the secure and the normal world is maintained. Now that we have covered the background, let me briefly introduce the motivation and the main objectives of our work. Currently, QEMU TCG supports the emulation of ultrasound, but KVM does not. which means the developer cannot run an RTVN with the acceleration of KVM. So we had an idea that we could virtualize trust zone CPU features at KVM and reuse the existing QEMU emulation on trust zone hardware to create a virtual trust zone environment for guest virtual machines. So the first goal of our work is to extend KVM to expose a virtual trust zone to the guest virtual machines. And the second goal is to set up an RTVN with our modified KVM and QEMU. By doing so, we can demonstrate the ability of our virtualization framework more clearly. Then I'll talk about the design of our approach. The first challenge we met is that guest VM can only execute in EL1 under KVM architecture, which means the instructions which should be executed in ELC are considered as sensitive instructions in our design, including exception return and move with ELC system registers. Those instructions may cause undefined behavior when executed at EL1. Although SNC should be executed at EL1, but it needs ELC system registers to save and restore the CPU context. So we still consider it as a sensitive instruction. And there is a host instruction, often used for semi-hosting code in ARM64. It's also considered as a sensitive instruction, since it may cause the CPU to stop from executing. To manage those sensitive instructions, the most common strategy is to trap and emulate them at KVM. However, not all sensitive instructions would be trapped to KVM. For example, exception return and host instruction may not be trapped. So we adapted a para-virtualization method to replace all of those sensitive instructions in the guest VM with hypervisor code. By doing so, we can force those sensitive instructions to be trapped to EL1 and allowing KVM to handle them. As I previously said, guest VM can only execute in EL1, which means we need to create a virtual ELC environment for those firmware which need to be executed at ELC. This includes creating a set of virtual ELC system registers. So I would like to introduce how we virtualize ELC system registers and how they work. One important observation is that most of the ELC system registers are also banked at EL1, including SPSR, BBAR, STLR, and so on. Which means we can simply virtualize ELC system registers by leveraging the equivalent EL1 system registers. Here's how it works. We simply replace all accesses of ELC registers with their EL1 equivalent registers in guest VM. For example, if the guest VM attempt to access SPSR ELC, we will replace it with SPSR EL1. And here's a simple graph which shows the key concept of our virtual system registers design. As you can see, we multiplex virtual ELC and virtual EL1 system registers onto physical EL1 system registers, which means we create a virtual ELC and a virtual EL1 environment based on physical EL1. And we maintain a virtual system register data at KVM, including EL1 and ELC registers. When the CPU changes the exception level, we need to put the correct virtual registers onto the hardware. For example, if the CPU makes an exception return to go back to EL1, KVM will save the virtual ELC registers and then restore the virtual EL1 registers onto the hardware EL1 to ensure the system state is correctly saved and restored. In addition to the registers that exist at both EO1 and EO3, there are a few registers that only exist at EO3. These registers, such as SCR EO3 and NDCR EO3, play a crucial role in managing the security state and debug configurations of the system. Currently, because these registers have no direct equivalent registers in EO1, our design cannot multiplex it on the hardware. So instead, accesses to these EO3 exclusive registers are replaced with hypervisor code. And KVM can keep tracking the state of these registers, which means the guest VM can also update and check the state of these registers in KVM. But the state of these registers will not affect the real hardware. Another key challenge in our approach is emulating sensitive instructions like secure mind code and exception return, which may cause the changes of exception level. So next, I'll introduce how these two instructions are emulated in our approach. Let's start with the emulation of SNC. When the SNC instruction is trapped to KVM, we first set the current program counter to the virtual EOR EO3. This ensures that we can return to the correct address when the exception handling is complete. Next, we set the current process state to the virtual SPSR EO3. This includes saving important information like condition flags and processor mode, so that we can correctly restore the system state after the exception handling. After that, we set the current program counter to the virtual VBAR EO3 with the corresponding offset. This step redirects execution to the EO3 exception vector table, allowing the system to handle the SNC as though it were operating in EO3. And finally, as I previously said, we need to perform a context switch to save and restore virtual system registers. In SNC, KVM saves the current virtual EO1 registers and then restore the virtual EO3 registers onto the hardware EO1. By following these steps, we can accurately emulating the behavior of an SNC in our virtualized trust zone environment. Then it comes to how we virtualize exception return. The handling of E-rate in our implementation follows a similar approach to that of SNC, which just simply restores the state set by SNC. First, we restore the program counter from the virtual EOR EO3, and then we restore the process state from the virtual SPSR EO3. They were both set by KVM during the emulation of SNC. Finally, we can perform another context switch, but this time we save the current virtual EO3 registers and restore the virtual EO1 registers onto the hardware EO1. And also, to support our virtualized trust zone environment, we made several key modifications to KVMU, particularly for emulating the secure memory and handling I/O operation. First, we added a virtual secure memory region within KVMU to emulate the secure memory used by trust zone. Within this secure memory region, we also mapped secure peripherals such as UART and general purpose I/O. By configuring secure UART, we are enabled to set up the console of the secure world of RT. Another important aspect of our KVMU modifications is how we handle semi-housing codes. Semi-housing allows a program running on an emulated system to communicate with the host environment, typically used for debugging and I/O operations. Semi-housing code in ARM64 is triggered by host instruction, which is considered as a sensitive instruction in our approach. So same as exception return, we need to replace them with hypervisor code first. Once the semi-housing code is trapped to KVM, we return the control from KVM back to KVMU to allow KVMU to take over and handle the semi-housing request. In KVMU, we leverage the existing TCG semi-housing handler. This means we didn't modify the semi-housing handler, we directly utilize the TCG semi-hosting mechanism to handle those semi-hosting calls. By incorporating these modifications into QEMU, we have created a more realistic emulation environment for trust zone. Next, I'll introduce the pre-virtualization detail of UpT. Most modification we made to UpT is about the untrusted firmware, which is the firmware of UpT. It is responsible for the boot process for UpT, including initializing the hardware, managing the security features, and loading the UpT OS into the secure world. In addition to managing the boot process, untrusted firmware is also responsible for handling SNC for UpT, and thus managing context switching between the secure world and the normal world. Untrusted firmware consists of several bootloaders, each playing a different role in ensuring the secure initialization and operation of the system. The first stage of the boot process, bootloader 1, is responsible for initializing the early hardware components and setting up some critical security features. Normally, bootloader 1 should be executed at EL3. So in our design, we need to replace all the instructions which will access EL3 registers with its EL1 equivalent. After the initial setup, bootloader 1 will execute an EWRITE and go back to secure EL1. Then bootloader 2 takes over to load and verify subsequent bootloaders and system software. Since in our architecture, bootloader 2 will run in EL1, we don't need to do many modifications to bootloader 2. Bootloader 3.1 is the core of untrusted firmware. It is a runtime firmware responsible for handling SNC and managing context switching between the secure and the normal worlds. Since bootloader 3.1 also runs at EL3, same as bootloader 1, we need to replace all the instructions which will access EL3 registers with its EL1 equivalent. And the next stage is bootloader 3.2, which will load and initialize the UpT OS in secure EL1. Since bootloader 3.2 runs at EL1, no specific modifications need to be done here. Finally, bootloader 3.3, which is U-boot in our context, is responsible for loading and initializing the normal world OS, usually Linux. And as the same as bootloader 2 and bootloader 3.2, no specific modifications need to be done here. Yes. After all the modifications we made to UpT, we successfully set up an UpT VM on our virtualized trust zone with QEMU KVM. So next, I can present the performance evaluation of our implementation, and here is the environment setup. The evaluations are performed on AVA developer platform with Neoverse N1 CPU. The Linux version of our modified KVM is 5.15, and the UpT version is 4.0.0. To evaluate the performance of our implementation, we measure the execution time of 7 different trusted applications in an UpT VM. These applications are provided by UpT in the UpT examples repository. The first 2 trusted applications, ACipher and AES, can help us evaluate the cryptography performance in our virtualized trust zone. And Hello World, it is just a simple application which can serve as a baseline to measure the transition time between the secure and the normal world. And secure storage, it helps us to evaluate the performance of secure data storage operations. And the last one, plugins. This application interacts with the Linux system log service as a plugin. It helps us understand the ability which the secure world can call a Linux service, can call a normal world service as a plugin. And here are the results of our evaluation. We additionally evaluate on QNU TCG with the stand-up-T version for comparison with our KVM approach. In both environments, we evaluate the execution time of 7 trusted applications I just mentioned. And as you can see, in most applications, our virtualized trust zone on KVM is about 10 times faster than TCG. Except for the plugins application, since this application invokes Linux system log service, we believe that our operation dominates the performance. So the execution time of it didn't show a significant difference between KVM and TCG. And at the end of my presentation, I'd like to talk about the future plan of our work. First, we aim to extend our approach to KVM-based confidential VM, which means we want to leverage existing confidential VM like PKVM or unconfidential compute architecture to provide strong memory isolation and protection to our approach. In addition, currently QNU hardware abstraction only supports a few trust zone-based devices. So we plan to extend QNU to virtualize more secure I/O devices. For example, we currently aim to virtualize the trust zone address space controller. The TZASC can define memory regions that can be accessed by the secure world while preventing unauthorized access from the normal world. By virtualizing the TZASC in QNU, we can better emulate secure memory access and improve the memory protection from the to the secure world. This is the end of my presentation. If you want to contact me, here are my linking and email. I am welcome for any further discussions. Thank you for your participation and any questions.
So you mentioned you had to change a number of the instructions to para-virtualize. I was a little unclear how you were doing that. Are you building a special version of trusted firmware in Octe, or are you patching it live as it runs?
We changed on a specific version of untrusted firmware. We didn't patch while it runs. We didn't do a runtime patch.
So it's a compile time change to build that version. You've made a fork and patched that manually.
Yes.
Right. Okay. Thanks.
Hi. Thanks for the presentation. So there's one thing that I think is might be a little bit fragile with the. I think when you were talking about replacing EL3 register accesses with the EL1 equivalent, I think that'll work in some cases, but as far as I'm aware, in a number of cases, the registers aren't quite the same between those. So, for example, you might have bits in the EL1 register or the other way around, which are reader 0, write ignore. And I'd be a bit worried that if you remap that access, you might lose some of the state, or worse, it might have an unintended side effect. So I think you might be better off using hypercalls for the registers as well, just so you avoid having to debug that, because it would be very difficult to figure it out.
It depends on different registers. Some registers in EL1 and EL3 have different structure. Maybe in EL3 it's a 32-bit, and in EL1 it's a 64-bit. So we check it in KVM while KVM prepare the exception level context switching between EL1 and EL3. We do a transformation between the correct structure for EL1 and EL3 registers.
Right, I'm just saying that the CPU might not offer all the storage that you need, so you could lose bits in some cases.
Oh, yes. Yes.
Thank you for the presentation. I have a question that is not for you, but it's more from the people that know the inside of ARM EL3 design. What is the reason why the hypervisor cannot optionally trap SMC and ERET, if you know?
It's supported. It's not in the base architecture, but it's supported. You got it with nested and with FGT as well. Have you considered? Have you gotten to the point where you've modeled security states in the GIC? Because it also applies to system IP as well, and the GIC is an example of something in KVM where you might need it.
Currently, we didn't consider the security stat in EL3. Yes.
Did you consider at some point to run the trust zone firmware in EL0 instead, so that you wouldn't have to modify it because you would be able to trap everything, including current EL, instead of doing binary modification?
I'm sorry, did you mean that we didn't?
So you could run the trusted firmware, basically what was at EL3, run it at EL0 instead. And all your privileged registers will be trapped.
Yes.
Including the current and exception level. Do you think that would be realistic, or the performance impact is too big?
Oh, I don't know that exception return could be trapped if we didn't replace it.
So for instructions that undef at EL0, you actually can take that to EL1, and if you could run like a little bit of shim code perhaps at EL1, then you can figure out how to route it from there and emulate the instruction. And then you could do your hypercalls from the EL1 shim that you're running into KVM or. Yeah.
Yes, you're right.
When you context switch from the secure and insecure world, do you have to change the page tables as well, or do they have the same view of memory?
Yes, the page table is maintained by the RTOS itself, and we just need to, or the RTOS will change the page table based registers.
I mean the stage 2 page tables, because they might have a different set of.
Stage 2 page table,
I guess my question is, like, I would expect when you do a context switch, you need to flush all TLBs because the page table may be different at stage 2.
Yes,
I don't know
we
if
will
you
flush
have
the TLB, but we didn't do stage 2 page table switch.
So slightly related question. Normally from the secure side, you are able to get a non-secure mapping. So you can, from the secure side, access non-secure memory. I was curious how you made that work.
And in our current implementation, we didn't do a lot at memory protection. Our work is just simply a proof of concept that we could virtualize trust on CPU features. Yes, as I previously said, in our future work, we may extend our approach to some of existing confidential VM to which that they can provide memory protection to our approach. So, thanks for your participation.
We are almost done. For millions of years, humans have asked the question, is OVMF too slow for serverless confidential computing? Before I answer that question once and for all, I want to say thank you to some people at AMD, Tom and David and Mike, for giving me some big pointers on this, and also to my colleague Chris Porter, who helped me through a lot of the work here, and I would have lost my mind without him. So you'll see why, probably. I want to give a few disclaimers. First of all, I should apologize for having a somewhat dramatic title. I'm not actually going to be making any really big claims in this talk. I also want to say that you might detect some undertones of frustration with OVMF in this presentation, but I actually like OVMF. I think it's cool, and none of this is intended as a slight at that project. Also, I wanted to point out that this is not really a talk about serverless. So if you don't like serverless computing or you don't know what it is, don't worry. I don't really like it either. This is really just a talk about booting VMs and trying to do it kind of quickly. And the last thing is that this talk has some audience participation, and it's mandatory. But it'll be fun. So just be prepared. Try and pay a little bit of attention so when we get there. OK, so why am I here? Partly because of these two papers. There's other contributing factors in my life too, but mainly it's these two papers. One of them is this from Carlos Segarra, a person I know, who was looking at doing serverless confidential computing on top of this confidential containers project that I've been involved with. This other presentation is from Ben Holmes, and this was actually supervised by Dan Williams, not the Dan Williams that you guys may have bumped into at LPC this year, but it's the other Dan Williams who you actually may have bumped into at LPC last year. Either way, both of these guys were looking at the performance of confidential computing in serverless. This is kind of a tough nut to crack. There are a lot of issues with serverless. First of all, in serverless computing, you often do some sort of warm start. You often try and not boot things as many times as you might otherwise. And doing this with confidential computing is kind of annoying. There might be attestations in the way, for instance, you might have a guest that's already sort of linked to one client. Cold starts are also slower and more complex, unfortunately. That's, again, what I'm really going to be talking about in this talk. But I do want to also mention that usually starting a lot of guests at once is slow. And this is where I have to say that we're into the AMD-specific territory in this talk. Both of these papers identify this trend, which you probably already know about, which is that starting a bunch of guests tends to scale linearly. This is because pre-encrypting the memory is serialized at the PSP. This is really not great for serverless. And in fact, these two graphs might answer the title slide already, but we're going to keep going and talk a lot about cold starts. So both of these papers evaluate cold starts. I should point out, though, that neither one of these papers is really about evaluating OVMF. Both of these papers are doing other things. Both of them care about measurement. You might know a little bit about like this bootstrapping thing, like this SEV hashes thing that's going on. And both of these papers actually point to this a little bit. You can see the OVMF measure verify stage over here and the green thing over there. That's the verification of the hashes. But in my talk, I'm not talking about measurement. I'm really just going to be talking about boot time, and I'm not going to be talking about the AMD SEV firmware package either. It's worth noting that these two papers have different configurations for their guests. They're using different kernels. This one is using SEV-SNP. This one is just using SEV or SEV-ES. So there's a lot of stuff that's different here, and in some ways that's not too rigorous. But I also think it's fair to ask this question kind of generally. Like if a user shows up, or if someone shows up and uses this thing with whatever configuration they might find, should they expect it to be a good experience or a not so good experience? And from these two graphs, you might say it's not going to be that great, because both of these papers identified some interesting delays that you might not expect. Look at this time, 6 seconds to boot a guest. Keep in mind these graphs, some of them include the kernel booting, which my graphs do not. Some of these also involve what goes on before you start the guest, which my graphs that you'll see shortly also don't. So Ben found some overhead in the BDS phase, the boot device selection phase. That's the crosshatch guy over there. And Carlos found some overhead in the Dixie phase. Okay, now for the big reveal as to what I ran into. So first of all, I want to point out that I did some of this testing on an oldish kernel, but I also have results on the new kernel, the upstream one, coming soon. It's going to be sort of interesting to compare these, because for one thing, this version of the kernel has huge page support, and the one that we're going to be looking at later does not. So think to yourselves, how is that going to look? But let's cut to the chase. For my results, SEV, well, no SEV is the top over there. Then we have SEV and SEV-ES, and all of those look fine. Let's face it, that's okay. But when we start getting to SEV-SNP, That's not great. So we'll talk about what happened here. First of all, though, if we do a quick comparison, Ben also had a problem in the BDS phase, right? So maybe I'm running into the similar thing that he's running into. Nobody had this issue in the sec phase, and spoiler alert, I don't know what causes that. Yeah, in general, some alignment. Also, yeah, Carlos's slowdown in the DXE phase, I could not replicate that. I suspect it's attached to some particular device. But yeah, last thing to mention here is that his configuration and mine are somewhat similar because we both were basing this somewhat off of Kata/confidential containers. So maybe he had some extra device that I didn't, I'm not sure. But don't worry, we will get into what is slowing down the BDS phase. And I think I have some answers. But before we get there, I want to talk a little bit about methodology. And this can double as advice to anybody who finds themselves debugging OVMF. There's a couple of different things you can do. Some of them work okay. So OVMF has support for a debugger, for instance. You can connect GDB to it, but not if you're using confidential computing, usually, at least not with a lot of messing around. So I didn't do that. OVMF ships with some EFI profiling stuff built into it, but the granularity was not right for my project, so I didn't use that. Printing, hey man, printing stuff, everybody's favorite method of debugging, that's what I did. In particular, I printed out the performance counter all over the place. There's a few things you need to be careful with here because printing does create more VM exits. So I introduced a new debug level in OVMF, so it would only print out my profiling things. And then I also checked how many VM exits I was getting to make sure it wasn't going through the roof. The performance counter in OVMF can be useful, but there are places you can't use it. In those places, you might be better off using RDTSCP, although that can be a little bit more difficult to work with. And this is one of the reasons why I was not able to get to the bottom of what's going on in the sec phase. That, and I ran out of time. Maybe next year, we can have this conference like a week later, and then I have a little bit more to show you. But anyway, there's also KVM tracing. So if you know what exits you're looking for, you can see if there are more of them. This wasn't very useful for me because I really didn't know what I was looking for. And it turns out that the stuff we see wouldn't have actually caused more exits necessarily. So, interesting. There's also the EFI shell. This is a really good thing to know about. If you're working with OVMF, you can boot into this EFI shell and check out some stuff that you really are going to have a hard time finding anywhere else. And we'll look at a little bit of that later. Fuzzing, some people have done this to OVMF. I didn't do it, but based on some things I found, this might be a good thing to continue doing, especially on certain interfaces. The final thing you can do is read the spec. The EFI spec is a mere 2,000 pages, and it's really exciting. But actually, the tip I'd give you is that the driver writer's guide provided by EDK2 is actually really good. Unfortunately, it doesn't have anything to do with virtualization, but it gives you a pretty good overview of what OVMF is doing. Okay, so the first thing you're going to think about when you're talking about overhead for SCV S&P is that it's got to have something to do with memory p-validate, right? Spoiler alert, nope. So there's a couple places where this happens in the guest. I won't go through all of this exactly, but there's basically 5 places. You'd think it'd be more, but not that many places in OVF where it happens, and none of them are part of this graph. By the way, I know you might be thinking, wait a second, you have the slowdown in sec, and there is p-validating going on in sec. I checked, it is not what is causing that blue, really big blue bar over there. So p-validate is not the culprit. Let's break this graph down. By the way, I adjusted the scale of the graph. I know it was so annoying that it ran off, but this is equivalent. But this is showing the phases a little bit differently. So that was all the standard OVMF phases on the previous slide. And this shows us the BDS phase. So the blue is everything before the boot device selection phase, which you might not really expect to be slow, but turns out it is. And then these are different parts of the boot device selection phase. And this maps to these parts of the source. So these are relatively small functions that are causing pretty big problems. And I have no idea if you can read this from where you are, but they have something to do. This one is EFI boot manager connect console variable. Interesting. We call that twice. And over here, platform manager, boot manager before console. That function does a lot of things. Neither one of these things off the top of my head I expected to be particularly slow, and I was a little bit stumped for a while. So I thought maybe I should just try to systematically remove some devices and see if I can get the results to change, and they do. So here's where the audience participation comes into play. One of these devices made the graph go from the left, which is what we were just looking at, to the right. Kicking out one of these made OVMF boot significantly quicker. Do you think it was A, this scary network device, B, this seemingly innocuous NUMA command, oh gosh, C, SCSI, oh man, we've got some heavy hitters here, or is it D, VirtIO RNG included as a joke, or is it? Okay. Who's for A? You have to vote, remember? Who's for B? Okay, Numa. Okay, who's for C? Anybody? Anybody for D? Okay. Yeah, the answer is D. So, first of all, I got to tell you guys, you should not be using VirtIO in a confidential guest. And one takeaway from this presentation is that we need to update CATA/confidential containers to not do this. And we should do that ASAP, I would say. But you might be wondering, why are we even calling VirtIO? How is this even involved? And it comes down to, well, in particular, what does it have to do with connecting consoles, right? Well, if you want to know all the details, you can look at section 3.15.3 of the driver writer's guide. It tells you about how OVMF goes through and connects the consoles. The thing to keep in mind, really, the Cliff Notes version is that OVMF is not very enlightened, and it knows something about the device tree, but it doesn't really know what any of these devices are, and it basically is going to end up trying to bind most of the devices that it has to most of the drivers that it has. So even if you don't even have a VirtIO device, that VirtIO driver binding code is going to be called a lot. And when you go to connect the console, what you're doing is you're looking at this console variable, and it's going to be a device path, which you're basically going to iteratively parse, and you're going to end up calling the devices, a ton of device drivers, a lot. Okay, but why is VirtIO actually slow? And the answer here is that it isn't. So if you actually profile the VirtIO code, the device binding code, you'll find that it's not slow. But when it is enabled, something else is slow. This is not great. But here's where the console came in. So again, I don't know if you can read this, but on the left, we have, this is the EFI console. It can give you a list of all the devices that you have. It can also tell you about the device tree. It's great. It's useful. It can tell you about your EFI variables too. We'll look at that a little bit. But yeah, so on the left, we have without VirtIO enabled. And on the right, we have with VirtIO enabled. And I don't know if you can read this, but right here, there's an iPixie device. So when we enable VirtIO, we get iPixie. That's interesting. Okay. I went through iPixie and profiled that. iPixie is not slow either. Anybody hazard a guess at what these things have in common, though? VirtIO and iPixie? The answer is SCSI. So it turns out the multiple choice question was kind of a trick in some ways, because that SCSI option does have something to do with it as well. For some reason, this is slightly odd dependency management, but for some reason, when you enable VirtIO, you get SCSI, and you also get iPixie. And most likely, SCSI depends on VirtIO, and iPixie depends on SCSI, or something like that. But this is a little strange. So this is one of these OVMF quirks. Okay, so why is SCSI slow? And it is. You can go through and profile it, and you'll see, yes, finally, all of these cycles I've been searching for, they're eaten up right here. And in fact, they're eaten up in that block of code, which on the surface doesn't look too bad. Why is this slow? Well, because it is setting a lot of EFI variables. It's modifying the NV data. And that is what is slow. Finally, we get to the root cause, sort of. Now, why was that slow on S&P, but not on SEV? Well, maybe it's actually because of a bug where SEV-ES fails to use the QEMU Flash driver. This is where we start to enter a lot of kind of strange territory, though. Okay, but before we go any further, I want to talk about the new kernel. I think that's what's on the next slide. We'll see. Yes. So on the new kernel, this problem was solved, right? So hopefully I didn't just waste everybody's time, but I do think that there's a couple of good things to talk about here. Why was it solved? I'm not entirely sure, but I think it is possible that it's because we no longer have read-only mem slots for these SVMs, where we used to, and that when we were using the NV data in the past, it would have been assigned to a read-only mem slot, and then when you try writing to it, you have to do some messing around, essentially. That's my theory. But yeah, there's, I think, some important things to keep in mind here. First of all, this new graph tells us something about huge pages support, right? So the sec phase, which is in this magenta color, is slower. But it's actually interesting that it's much less significant than this overhead of setting the EFI variables was, which is not what I had expected at all. Now, this is not to say that huge page support is not important, because you're going to use it a lot more throughout the rest of the boot. This is only OVMF, which is really not dealing with that much memory. But you almost certainly want this for the kernel. It's going to be key. But one thing to keep in mind is be careful. This is a hard space to optimize in, and there might be things that you wouldn't really expect to slow down the guest a lot that could be very significant, and EFI variables is one of those things. There also is some ongoing discussion about the flash stuff, right? So I saw, for instance, there was one of the commits in the S&P series was about using pflash, was about using the new BIOS flag with pflash, right? And this was ultimately dropped. I think because people thought it was just kind of weird to use BIOS and pflash both, which, let's face it, it is. But there's still some discussion here about what are we actually supposed to be doing with these QEMU flash things. Some people have talked about like these should be provided by the SVSM, or there's sort of a fundamental issue here. You know, in SEV we don't measure these things, right? If you specify like a flash 1 drive for like legacy SEV, we don't measure that, and that's interesting. I think the idea is that you don't want this thing that's volatile to change your measurement and screw it up, but it's possible these things are security sensitive. So there's a little bit of a puzzle there that I think we've never exactly solved. Just for reference, these are this is the NV data. So again, this is from the EFI console. You can print out the NV data, and this is what I have for my guest. And actually, none of these things are security sensitive at all. So you know, maybe who cares? I know there's something called key 1 here and key 0, but those keys are like the hotkeys you use to get into the BIOS. They're not like secret keys, although secure boot keys can be stored here, so you need to think about this. From my guest, I think the most malicious thing that you could do is modify this to change the system language to check. I think that qualifies as an attack, but somewhat easy to undo that. There are some things I think we do need to take a much closer look at that with QEMU Flash, though. Yeah, someone who knows a lot more about Flash than me, I think should really go through this QEMU Flash driver, because I think there are some gremlins here. And one thing that's notable is that when we are using the new upstream kernel patches with SEV S&P, we still hit the QEMU Flash driver, even when we're using the BIOS flag. I'm not sure we really should be, and it seems like we're still trying to write to Flash. I also found cases where writing to this Flash would end up with some corrupted variables, because I don't know if you can see this, but at the end of writing to Flash, we write this read array command to set the Flash back to being like, that's like, hey, I'm done writing, essentially. You want to give Paolo a mic? Oh, no. What? Did my computer go to sleep?
So I'm not sure I remember correctly, but I think what happens is that with SMP, there's no memory, read-only memory, so it becomes pure MMIO. So it becomes slower to read, but you can still write to it, because writes were MMIO also before. Now the reads and writes are both MMIO. The difference is that with the read-only memory support, you can execute in addition to reading, while with SMP there's no memory slot at all, so you cannot execute from it. So you will hit it, and you will also hit it more slower, because you will hit it for reads and not just for writes.
Yeah, interesting.
So you'd better not use Flash at all, and in this case, you just don't have the memory.
Yeah. OVMF is
I'm not 100% sure, but it's plausible at least.
Yes. There's a lot of different cases here for SEV with one Flash device, with two Flash devices with it read-only, with it not. There's a lot of cases here. Some of them I don't think are behaving quite correctly. For instance, there are times where there is no Flash and it's backed by memory, and we're still calling this code, and we're writing this read array command into memory, which corrupts some of the variables, which I don't think we want to be doing that. In fact, I'm not sure that we should be calling the QEMU Flash driver at all. And for SEV-ES, we don't use it, but I think the reason why we don't use it is actually because there's some weird bug in the initialization phase where the header, the firmware volume header that we expect to find at the certain memory offset gets trampled somewhere during boot, during SEV. So yeah, it seems like we're doing it correctly for SEV, but I think it may actually be a bug that's happening. For S&P, I'm not sure we're doing it correctly. So anyway, moral of the story is, like I said, someone who's a little bit better versed in Flash might want to take a look at this QEMU Flash driver and just make sure. And there is also still some discussion going on about what are we even doing about Flash in the first place. You know, is the SVSM going to handle this eventually? Do we want these things to be measurable? There's a lot going on here. Okay. Conclusion. So, oh right, I had this big bold question that I was going to answer in this thing. Well, the answer, I hate to do this to you guys, is yes and no. I think honestly that the big slowdowns that we saw in those papers are not necessarily inherent issues, and I think they can be I think we can get around those things. And if we're looking at like 6 seconds to boot like an S&P guest, that's too long, and that's probably a bug. And OVMF is not going to result in that. That said, in serverless, every single byte of your firmware does count. We talked about the overhead of the pre-encryption phase and how that's serialized. So, you know, there is ammunition for saying that you would want to use something else. To me, I think the biggest overhead, by far the biggest overhead when using OVMF is actually none of this stuff. It's the overhead of using OVMF as a developer and trying to put optimizations in it and trying to understand all of the different cases, because that is pretty slow. And OVMF is inherently a complex program. It's doing something that is complicated, but there is also other firmware that maybe cuts some things out. So something to think about. There are also a few concrete things to fix. So we got to remove VirtIO RNG from Kata. That should not be there. There's also a few configurations that QEMU will let you use that I'm not sure are really supported. Like with the new kernel, you can use the BIOS flag with SEV and SEV-ES, and everything kind of seems to work. But if you do it wrong, that's one way you can get this weird sort of writing into writing these commands into memory, thinking that it's Flash thing, which I don't think we really want. It also might be good to try and document this a little bit better, just to make people slightly more aware of like what you're supposed to be doing. Here again, somebody else should take a quick look at this QEMU Flash driver and just see if it's sane. And then also, I would like to get to the bottom of this sec overhead at some point. And if anybody has any suggestions about what they think that might be, please let me know. I think this is the last slide. I forgot to put a question slide, but you may now ask any questions that you have.
So, really good work. I agree with your statements, like OVMF isn't inherently slow. It is surprisingly complex. And a phase you shouldn't be executing in serverless. Like the whole point of serverless systems these days, at least, like now that we have done them for the last decade, is to move to a snapshot model. So what we need to do here is we need to figure out how we can create a sensible SFSMP or TTX-enabled snapshot restore mechanism, right? So when that may actually be finally a valid use case for SVSMs, where we get an SVSM inside of our VM that then is able to on demand go and page my payload in. We just need to make sure that the hypervisor state, device state is also synced. The other piece, going back to the very, very early part of your presentation, would have been good to sync up beforehand. I did patch this a few years ago to provide an in-memory timestamp boot lock for OVMF, for EDK2. So you can basically, you get a, effectively in Linux, you then get in sys firmware boot lock, you get boot locks for every component that ran before Linux, and that includes EDK2. And so you just enable a debug build of EDK2, you tell it dump into this boot lock that's in memory, and then you get a fully timestamp boot lock that doesn't impact your boot times, but allows you to very fine-grain just do normal printf development, which is what we're all used to and love, right?
Yeah, that sounds like great work. And I agree, by the way, the SVSM Coconut is a lot smaller than OVMF, and something, I don't know if you'd call this like a warm start or whatever, but doing some kind of snapshotting thing like this is probably a good approach.
Okay. So was this slowdown just because of the VirtIO RNG device, or do you add some other random device and it still shows up? Is it the device thing itself, or this specific device?
Yeah, so to be totally clear, on the older kernel, which is not upstream, but on the older kernel, what the slowdown, the root cause was setting the NV data. So it's setting EFI variables. And anywhere you would do that, there would be some slowdown. Like you noticed that this presentation was mainly investigating the second part of the BDS phase. Didn't talk about the first part, but yeah, it turns out we set some other EFI variables in that section, right? So the place I ran into it was because SCSI sets a bunch of EFI variables. I think there's one called like number of attempts that it sets. And yeah, that was slow. And because of some OVMF weirdness, that SCSI code was being called when VirtIO RNG was there, but not when it wasn't.
By any chance, do you know what the VirtIO RNG backend was? If it was trying to initialize and VirtIO RNG, I don't remember the I mean, I wrote VertiRNG, but I don't remember the code right now on what it does on probe. But if the backend on the host reads from dev random, maybe the host doesn't have enough entropy and it has to wait. If you switch it to dev urandom, all of this should be faster. So
yeah, I tried both of those things. No difference.
All right.
And like I said, benchmarking the I benchmarked the actual like VertiRNG code for the probing and the binding, and it's not slow. So good job with your work.
Yeah. So regarding there's some logic there where I think for SCVES, if it was a read-only mem slot and then it did its normal probe to see if it was a flash device or normal memory that it could write to, it would basically shortcut it so that it would end up using MMIO instead, because those probes would try to write to the read-only mem slot, and that would cause VC, and then to get into an infinite loop. So there's some code there that says if I'm SCVES, just skip all these checks and just assume I'm a flash device. And then somewhere else in the code, when it actually does the writes, it uses MMIO VMX, GHCB calls to do the writes. But now, pretty late in the development cycle, on the QEMU side, on the kernel side, we disallowed the use of read-only mem slots. And that was one of the reasons that on the QEMU side, you now use -BIOS, because when you take that approach, it doesn't map it as a read-only mem slot. So I'm wondering now if you could just write to it like normal memory, and that would just make everything speed up, and you just treat it like normal memory. The flash would still be ephemeral and it'd go away, but that's sort of kind of by design right now. Yeah.
Yes, I think we should be treating this as normal memory. The one thing to keep in mind is that OVMF also has a fallback emulated NVData driver, and QEMU Flash, yeah, it's going to have this special exit for the VMG exit thing to do the MMIO. I don't think we should really be getting into that code path at all. I would be fine with just falling back and using the built-in OVMF fallback thing. Yeah, that's what that would result in. Yes.
And maybe when we do the -BIOS, instead of doing the full ovmf.fd, you just do ovmf code.fd, and then it'll just use RAM completely, I think, for the variables.
The ephemeral build of OVMF is what we do in Fedora and RHEL for Sev and ZVS right now, because, as you say, the NV bit is not measured, so you don't want it there at all.
Yep.
From 0% to 100%, how much is the confidential warm start a migration problem? Like something that you basically need to sort out how to load memory as if it was a migration, and then, however, still get the same attestation report as if it was a cold start.
Yeah, so I guess the question is, how similar is the warm start to migration? It depends on, it depends on exactly what we mean by warm start. I think maybe snapshot is a better term, which is what Alex mentioned. And yeah, snapshotting in some ways is pretty similar to migration. There are also potentially much simpler ways to do something for serverless where you just start a guest ahead of time. Here's where you need to be a little careful with the attestation, because that will be sort of scoped to the boot time. But maybe if you know that one client is going to be booting a bunch of functions or whatever, and then you boot up a bunch of guests for them ahead of time, you can do a type of warm start, which is way simpler than like doing a snapshot. Yet, how similar is snapshotting to migration? The thing that I actually think it's maybe more similar to is some of the stuff we were talking about from like booting from the SVSM earlier, or like booting even Alex's talk to some degree about booting like a different kind of guest. I think is somewhat similar. Because the snapshot also has the advantage that the thing that actually does the decryption can be very small. You can put the actual data unencrypted, like encrypted but in shared memory, encrypted with a kind of transport key. And this way you can then check that it's actually the firmware that you want, but you only have to pass to the ASP a small
decrypting trampoline, and therefore you also kind of fix the launch update serialization problem.
Yeah, I think we're out of time here, but I would just say as the final thought that I think stack collapse, like what you're talking about, is very good. And ideally, if you care about serverless, you shouldn't really be using OVMF at all. You should be taking as many shortcuts as possible. And I think that's something we should be trying to look into as much as possible. Thanks, everybody.